The Whirlpool Galaxy looks like a cosmic masterpiece, but it's also a machine. Gravity winding its spiral arms tight, gas collapsing into stars, and something unseen pulling the strings. What's really happening at its centre, and could that hidden engine decide whether a galaxy lives, evolves, or tears itself apart? 23 million years of travel end in a single photon striking our detectors, carrying a message older than our species. In the Whirlpool Galaxy, that message is written in arcs of starlight, and in forces we cannot see. This is 137, a descent through a spiral that seems calm, yet never truly rests. Every curve is a record of motion, every luminous knot a brief flare in a long accounting of matter and time. We will read that record the way astronomers do, by changing the light itself, shifting from visible beauty to infrared heat, from radio whispers of hydrogen to X-ray flashes from violent plasma. At this distance, the Whirlpool is not a place we visit in the present. It is a scene preserved, delayed, and still arriving. The galaxy's grand design becomes a puzzle of cause and effect, where the same pattern can mean very different physics depending on the wavelength and the scale. A dust lane can be a boundary, a birthplace, or a scar. Its meaning changes as we move closer. Begin with the spiral arms, and the story seems straightforward. Gas gathers, stars ignite, clusters bloom. Stay a moment longer, and the simplicity breaks. The arms are not fixed beams of matter, but organized waves moving through a rotating disk, sorting clouds like traffic and setting clocks only a few million years long. Those clocks matter, because star formation is inefficient by nature, and the galaxy survives by resisting its own tendency to burn through its fuel. Then come the forces that do not announce themselves in starlight. An extended halo of unseen mass steadies the disk and shapes the orbits that keep the spiral coherent. Tidal influence from a smaller companion tugs at the pattern, sharpening some arcs and loosening others, turning a beautiful geometry into a living interaction. What looks like symmetry can be the temporary alignment of competing pulls. Follow the rivers of gas and dust and you find phase changes everywhere. Atomic to molecular, warm to cold, diffuse to dense. Shocks compress clouds, turbulence frays them, magnetic fields thread through the chaos, and gravity waits for the moment conditions finally allow collapse. In these regions, the galaxy is neither serene nor explosive, but regulated. Balancing cooling against pressure, formation against disruption, growth against loss. Where stars are born in groups, their brief brightest members begin to reshape the environment almost immediately. Ultraviolet light carves cavities, winds inflate hot bubbles, and supernovae arrive on schedule, turning stellar nurseries into weather systems that can trigger new collapse or erase it. Metals and dust spread outward, changing how the next generation cools, fragments and forms, making the Whirlpool a chemical history as well as a dynamical one. But our path does not remain in the arms. The spiral also points inward, and that direction raises a harder problem. Matter cannot simply fall to the centre. Angular momentum is a lock, and the galaxy must find ways to pick it, through torques, resonances, shocks, and slow exchanges that trade rotation for inward drift. Along the way, gas can stall in rings, surge in episodes, or be redirected by patterns that only exist because the whole disk is in motion. As we approach the inner region, the stakes tighten with the radius. Orbits crowd, shear strengthens, pressures climb, and the same amount of mass can release vastly more energy when it reaches smaller scales. The nucleus becomes an arena where dust obscures, geometry deceives, and multiple engines can imitate one another, so certainty must be earned by converging evidence rather than a single image. Here, the Whirlpool's most consequential processes may be the least visible. This documentary follows the galaxy as a system, an ongoing negotiation between what shines and what hides. We will ask what physical processes build, sustain, and transform this spiral from its farthest arcs to its extreme centre, and what that teaches us about how galaxies evolve across the universe. The Whirlpool is not a postcard. It is a balance, temporary, dynamic, and exquisitely informative. Watch the patterns carefully because they are not decorations. They are the signatures of gravity, of gas cycling through states, of feedback that both creates and limits, and of a central region whose influence can extend far beyond its size. By the time we return to the full view, the beauty will remain, but it will no longer be silent. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We begin in the dark around M51, then peel back its hidden mass, its star-forming rivers, and its turbulent weather, and we spiral inward, step by step, until the centre forces the galaxy to reveal what it is truly doing. We begin with a destination that looks familiar, yet remains fundamentally unreachable. The Whirlpool Galaxy, M51, hangs in the northern sky like a diagram of order, two curling arms set against a velvet field of stars. It is also a system under stress, shaped by gravity and time, and never truly at rest. M51 is about 23 million light-years away from Earth. That number is not only distance, it is delay, because light has a finite speed and the universe keeps moving. The light arriving now began its trip when early humans were first spreading across Earth, long before writing, cities, or recorded memory. Every photon is a messenger that cannot update its story, and that limitation becomes our method. Looking at M51 means looking into the past. We do not see the galaxy as it is today, because today has not reached us yet. We see a fossil record written in starlight, filtered by dust, and stretched across intergalactic space. Subtle colours and contrasts that encode temperature, age, and composition. The image is a time capsule, and time is the hidden dimension of every frame, even when the picture feels still. In a wide shot, the whirlpool appears almost instructional. The core glows like a lantern, and the arms unwind with a measured elegance, dotted by bright knots that resemble beads on a string. Yet those knots are not ornaments, because they are clusters of massive young stars that burn hot and die fast. Even the dark lanes have meaning, because they are not empty space but dust-rich regions where light is being absorbed. This chapter sets the rules of the journey. We will move inward from the luminous spiral arms to the compact nucleus, following structure into increasing density and complexity. We will treat beauty as a clue, not a conclusion, because symmetry can be the signature of a physical process. We will ask what processes build and maintain this structure, and what forces can break it, distort it, or erase it. The whirlpool is not a single object. It is an interacting pair, locked in a slow gravitational exchange that has likely been unfolding for hundreds of millions of years. The main galaxy is Messier 51a, also catalogued as NGC 5194, and its smaller companion is NGC 5195, perched near the outer arm like a hand on a spinning wheel. Through telescopes, the bridge of disturbed material between them hints at a long history of close passes. M51a is classified as a grand design spiral galaxy. Its arms appear unusually crisp and symmetric, as if drawn by a careful hand, and that clarity is part of its fame. Historically, M51 was among the first galaxies where spiral structure was recognized clearly, helping shift nebulae from mystery objects into organized island universes. That appearance is not accidental. And it is not purely internal, because interactions can amplify patterns that would otherwise be weaker and more fragmented. The companion matters because gravity is not gentle at galactic scales. A passing mass can torque the disk, drive waves through it, and rearrange orbits over millions of years, even when the encounter seems slow. Tidal forces stretch material along preferred directions, and the disk responds like a flexible sheet, rippling rather than snapping. The result can be a sharper spiral pattern and bursts of star formation in compressed gas, especially where the wave steepens into a shock. We need an anatomy primer before we can go deeper, because the whirlpool's elegance is built from components with different histories. A spiral galaxy is built from a rotating disk, a central bulge, and an extended halo that reaches far beyond the visible light. The disk holds most of the gas and young stars, arranged in a thin plane where rotation dominates. The bulge holds older stars in denser orbits, often with a more randomized, puffed-up distribution. The halo stretches farther out, dominated by dark matter and sparse stellar populations, and it quietly controls the long-range gravitational field. The disk is where the spiral arms live. The arms are not fixed lanes of the same stars like paint on a record, even though they can look that way in photographs. Stars orbit the center differentially, with inner regions moving faster than outer ones, because gravity and angular momentum set different orbital speeds at different radii. If arms were made of the same material, they would wind up tightly and disappear, a classic problem that forced astronomers to rethink what a spiral arm actually is. So the arms are better understood as patterns. They are density waves, regions where matter bunches up as it orbits, much like a traffic jam that persists even as individual cars enter and leave. Gas enters the wave, compresses, and can form new stars when clouds become gravitationally unstable. Stars then drift out, while the wave pattern persists and moves through the disk, maintaining the spiral shape over long timescales. That distinction sets up our first tension. The arms look calm because we see them as smooth light, and our eyes are drawn to their graceful curvature. In reality, they can be shock fronts that squeeze clouds and trigger collapse, raising density until gravity takes over locally. Calm spirals can hide violent local physics, repeated across thousands of light years, and repeated again each time gas cycles through the pattern. M51 is an ideal laboratory for these questions because it is both near and well structured. At 23 million light-years, we can map details across the disk, separating star-forming regions from dust lanes with surprising clarity. Its interaction is clear enough to study, yet not so chaotic that the pattern is erased, making cause and effect easier to trace. It sits on the edge between order and disruption, where a small push can reorganize an entire disk. To understand it, we cannot rely on one kind of light. Each wavelength reveals a different layer of the galaxy, and each layer answers a different question about matter and energy. Optical starlight shows the distribution of stars and the bright knots of recent formation, especially the hot blue populations that dominate the visible glow. It also hides what dust blocks, and it can mislead by emphasizing what shines most, rather than what contains the most mass. Infrared light helps us see the dust itself. Dust grains absorb ultraviolet and optical energy, then re-emit it as heat, shifting the story into longer wavelengths that can pass through obscuring clouds. Infrared maps can trace where star formation is embedded and where dust lanes carve through the disk, outlining the spiral like dark calligraphy. Dust is both veil and blueprint, marking where gas has piled up and where the next generation is incubating. Radio observations extend the map outward. Neutral hydrogen, called HI, emits at 21 centimeters, a spectral line produced by a quantum flip in the hydrogen atom that is rare per atom but powerful in aggregate. HI surveys reveal the diffuse gas reservoir in the outer disk, often beyond the visible starlight, where the galaxy's influence still extends. They also show tidal distortions and streams pulled by the companion, evidence of gravity working at the larger scales. Millimeter observations track molecular gas, the immediate fuel for star formation. Carbon monoxide, CO, is used as a tracer because cold molecular hydrogen is hard to detect directly, and CO's emission lines are easier to measure and map. CO maps show where dense clouds concentrate along the arms and near the center, often lining up with dust lanes and shock regions. They reveal the supply lines feeding future stars, and they hint at how efficiently gas is being converted into stellar mass. X-rays show a different kind of environment. Hot plasma shines in X-rays, produced by supernova remnants, stellar winds, and energetic processes near the nucleus, where gravity and magnetic fields can accelerate particles. X-ray sources can mark compact objects, binary systems, and regions where gas has been heated to millions of degrees, far beyond anything visible in optical light. This is the layer where violence becomes unmistakable, and where the galaxy's energy budget becomes easier to measure. These tools are not optional, because galaxies are not transparent. Dust hides young stars in optical light, while infrared reveals them, and the difference can change our interpretation of where the action really is. Cold gas is invisible to the eye, while radio and millimeter bands map it directly, turning empty-looking regions into reservoirs of potential. The same region can look quiet in one band and explosive in another, and the truth is assembled from their overlap. The central question of this documentary begins here. What physical processes build, sustain, and transform the whirlpool from its arms to its core, and how do those processes remain coherent across such enormous scales? Which forces are visible and which are hidden, because much of the mass does not glow? How does a galaxy convert gas into stars while gravity reshapes the entire system? And how does it avoid consuming its fuel too quickly? The hook is that M51 looks like a postcard, yet behaves like an engine. It takes diffuse gas and concentrates it into clouds, and it does so repeatedly as rotation carries material through spiral density waves. It turns clouds into stars and stars into heavy elements and shock waves, enriching the interstellar medium with every generation. It stores energy in rotation, then releases it through interactions, feedback, and collapse, converting orderly motion into heat and turbulence. We also have to confront the role of dark matter early. The visible disk does not contain enough mass to explain how spiral galaxies rotate, a discrepancy that became undeniable once rotation curves were measured across many systems. Stars in the outer disk orbit faster than visible matter alone would allow, as if extra gravity is present where little light exists. That implies an unseen halo that dominates the gravitational potential and stabilizes the disk, shaping how the galaxy responds to every disturbance. Dark matter is not a decorative add-on to the story. It is the scaffolding that holds the disk together and sets the stage for spiral structure, even though it neither emits nor absorbs light in any conventional way. It shapes the rotation curve, which influences where density waves can form and how long they can persist, because orbital speeds set the rhythm of the disk. It also affects how the companion's tug propagates through the system, determining whether the response is a gentle ripple or a stronger rearrangement. Gravity is the architect, but gas is the fuel. Gas responds to gravity quickly because it can collide and cool, and those collisions allow it to shed energy that stars cannot easily lose. When gas is compressed, it can radiate energy away and become denser, moving closer to the threshold where self-gravity overwhelms internal pressure. That is why spiral arms and interactions matter, because they create the conditions for compression, and compression is the first step towards starbirth. Dust follows the gas and changes what we can see. Dust grains form from heavy elements made in stars, then spread through supernova explosions and winds, seeding future clouds with the raw material for planets and chemistry. Dust traces the cycle of matter through generations of stars, linking stellar death to stellar birth in a continuous exchange. It also blocks and reddens starlight, turning observation into interpretation, because what looks dim may simply be hidden. Time complicates every measurement. When we map M51, we assemble information from light that left at the same era, but from regions evolving on different timescales, and that mismatch matters. Star formation can change in a few million years as massive stars ignite and then explode. Orbital patterns shift over tens of millions, while interactions unfold over hundreds of millions, slow enough to feel permanent but fast enough to reshape a galaxy. Even within one image, we are mixing histories. A bright blue cluster signals very recent star formation, dominated by short-lived massive stars that will not survive long. A redder bulge reflects older stellar populations, where long-lived stars accumulate over cosmic time. Dust lanes mark where the next generation may be forming, still hidden, and the contrast between light and shadow becomes a timeline. The interaction with NGC 5195 adds another time axis. The companion's orbit has likely passed through the disk's outskirts, pulling out material and driving waves inward, and simulations suggest multiple passages rather than a single encounter. Each close approach can trigger new bursts of star formation, leaving rings, arcs, or enhanced arm segments as lingering signatures. The present spiral pattern may be a snapshot of a repeating cycle, and we are catching it mid-turn. We can describe the system in simple terms, but the physics is not simple. The disk rotates, but not like a solid wheel, because gravity and angular momentum distribute motion unevenly across radius. Inner stars complete orbits faster, outer stars lag behind, and that shear stretches structures over time. Gas clouds collide, fragment, and collapse, while stars mostly pass through each other without collisions, responding more cleanly to the overall gravitational field. That difference between gas and stars is crucial. Gas can shock and lose energy, so it piles up in spiral arms and in the central regions, where pressure and density climb. Stars keep their orbital energy more faithfully, so they trace the gravitational potential more smoothly, blurring rather than clumping. The visible spiral is partly a map of where gas has recently been forced to change state, from diffuse to dense, from stable to unstable. The arms are therefore not just decoration, they are sites where gravity organizes matter into lanes of higher density, and where chemistry becomes more complex as molecules form in shielded regions. They are also sites where feedback begins, because new stars emit radiation and winds that push back on their birth clouds. Massive stars end as supernovae, injecting energy and turbulence back into the gas and enriching it with heavier elements. This feedback can both trigger and suppress star formation. It can compress nearby clouds, nudging them toward collapse, or it can blow cavities that halt collapse by dispersing gas. Over time, feedback regulates how efficiently a galaxy converts gas into stars, keeping the process from running away too quickly. The whirlpool's apparent balance suggests a system near steady operation, but not guaranteed stability, because the next interaction or burst can shift the equilibrium. The center raises the stakes. Brightness near the nucleus can mean a dense concentration of stars packed into a smaller volume, raising the gravitational field and the frequency of close encounters. It can also mean accretion onto a compact object, where gravity converts falling matter into heat and radiation with extreme efficiency. Crowded orbits, strong tidal forces, and high gas pressures make the inner region qualitatively different, as if the calm spiral has been funneled into a narrow throat. We will not assume what powers the core yet. We will treat the nucleus as a question that must be tested with multiple wavelengths, because brightness alone is ambiguous. X-rays can reveal hot gas and compact sources, and they can hint at accretion or energetic remnants. Infrared can show dust-enshrouded activity, where optical light fails, and radio can trace jets or dense gas, if they exist. The journey inward is not only spatial, it is a descent through physical regimes, where the same basic forces produce different outcomes as density and shear increase. In the outer disk, gravity competes with rotation and low-density gas, and structures can be fragile. In the arms, shocks and compression dominate, and star formation becomes more likely. Near the center, tidal forces, shear, and extreme densities change the rules, and small instabilities can cascade quickly. To keep our bearings, we return to the basic structure: disk, bulge, halo, and the unseen mass that binds them, components that together determine what can form and what can persist. Spiral arms as waves that organize gas and ignite stars, leaving luminous traces that fade on predictable timescales. A companion that perturbs the pattern and may feed the center, turning a stable-looking design into an evolving experiment. These are the components of the machine, and each one leaves a signature we can measure. At 23 million light-years, the Whirlpool is close enough to study in detail, yet far enough to remind us what astronomy really is. We cannot touch the system, and we cannot speed up its clock, so we build understanding from fragments of light and careful inference. We infer causes from light, motion, and models, then test those in every band we can, looking for consistency across independent lines of evidence. The chapter ends where the real investigation begins. The postcard view is only the surface layer of the story, a first impression that hides as much as it reveals. Beneath it lies the scaffolding of gravity and dark matter, and the supply network of gas and dust, cycling through compression and feedback. From here, we move from appearance to mechanism, entering the spiral to find what drives it, and to ask what, in the darkness between the stars, is quietly shaping everything we see. M51's arms look like ink on a page, but the page is gravity, and the ink is motion traced over time. In Chapter 1, we met the Whirlpool as a pattern in light, shaped by interaction and time, and we watched brightness sketch a graceful two-armed design. Now we remove the glow and keep the pull, as if the galaxy were backlit only by its own mass. We ask what distribution of matter can hold a thin disk together, set its orbital rhythm, and let a spiral remain recognizable for more than a moment. A spiral galaxy is not defined by its stars alone, even when stars dominate the photograph. It is defined by the gravitational potential that guides every orbit: stars, gas, dust, and matter we cannot see. In M51, the luminous disk and bulge are only the inner trace of a much larger structure, like a lit shoreline around a dark ocean. The halo extends far beyond the visible edge, and its mass dominates the outer rotation where starlight thins to almost nothing. When we look at M51 in deep exposures, the bright arms fade into a faint outer disk, and then into a barely perceptible haze. That fading is not the end of the galaxy's influence, because gravity does not stop where the light stops. The true boundary is not a crisp rim but a gradual transition, where the density drops and the timescales grow long. In that dim regime, the halo's presence becomes easier to infer than to ignore. The first clue is motion, not appearance, because motion is a direct response to the total gravitational field. Astronomers measure velocities across the disk using Doppler shifts in spectral lines, turning the galaxy into a map of approaching and receding gas. A line is displaced slightly redward or blueward depending on whether gas approaches or recedes along our line of sight. By mapping those shifts across the face of M51, we reconstruct a velocity field and infer the underlying gravitational potential. The technique is conceptually simple, but the execution is meticulous, because every pixel carries both signal and uncertainty. Observers choose lines that trace specific phases of matter, and they correct for inclination, because M51 is tilted rather than perfectly face-on. They also account for instrumental calibration, atmospheric effects, and the galaxy's systemic motion through space. What remains is a pattern of velocities that encodes the mass distribution more honestly than any photograph. If visible matter were most of the mass, orbital speed would fall with radius, and the galaxy would behave like a scaled-up solar system. It would resemble planets around the Sun, where gravity weakens with distance and velocity drops as orbits widen. Many galaxies do not do that, and M51 follows the same rule with striking clarity. The rotation curve stays flat well beyond the bright disk, meaning orbital speed remains roughly constant as radius increases. A flat rotation curve is not a small discrepancy, and it is not a detail that can be patched with a minor adjustment. If speed stays constant, then the enclosed mass must keep rising almost linearly with radius, even where the light declines. In plain terms, the galaxy keeps getting heavier as you move outward, but it does not keep getting brighter. That mismatch is the signature that forced astronomers to separate mass from luminosity. To see why, imagine drawing a circle around the galaxy at larger and larger radii and asking how much mass lies inside. In a system dominated by a central concentration, most of the mass is already enclosed early, so orbital speeds drop. In M51, the curve refuses to drop, implying that the mass distribution remains extended. The outer disk is therefore not orbiting an inner luminous core alone, but a much broader gravitational structure. A flat rotation curve implies extra mass at large radii, and it implies that the halo is not a minor wrapper but a dominant component. That mass cannot be explained by faint stars, dust, or cold gas alone, because their observed quantities fall short by large factors. The simplest interpretation is a dark matter halo, extended and massive, shaping the potential that the disk lives inside. In this view, the visible spiral is a bright skin on a much larger invisible body. Dark matter is inferred from gravity, not detected by light, and that distinction matters for how we talk about evidence. It does not emit, absorb, or scatter in familiar ways, so it hides from direct imaging across the electromagnetic spectrum. Yet it leaves measurable signatures in orbital speeds, gravitational lensing, and the stability of disks. In M51, it acts as the scaffold that sets the baseline rotation and moderates how the disk responds to disturbances. The idea of unseen mass has a history that runs through the 20th century, and it grew from unease into necessity. Early hints came from galaxy clusters, where visible galaxies moved too fast to be bound by the light alone. Later, rotation curves of spiral galaxies made the problem local and unavoidable, because the discrepancy appeared within single galaxies. By the time observers mapped many spirals, the pattern was consistent. Flat curves were common, and luminous matter was insufficient. This invisible halo is also a cosmological fossil, because it reflects conditions from the early universe. In the first few 100,000 years after the Big Bang, matter and radiation were tightly coupled, and small density fluctuations were imprinted across space. Dark matter collapsed first, because it could not radiate energy away, so it formed large halos that grew by merging and accretion. Ordinary gas fell into those wells, heated, cooled, and settled into rotating disks as it lost energy through radiation. The disk is therefore a consequence of cooling and angular momentum, and both are conserved in different ways. Gas that falls inward cannot drop straight to the center, because it carries rotation, inherited from the tidal torques of early structure formation. As it contracts, it spins faster, and centrifugal support increases, so the gas spreads into a thin plane. Over time, that disk becomes the stage for spiral structure, star formation, and the slow rearrangement of matter. Visually, the disk's thinness is one of the most striking clues that cooling worked efficiently. A hot, pressure-supported system puffs up into a spheroid, but a cooled system settles into a plane. In M51, dust lanes carve dark filigree along the arms, and the disk's geometry becomes obvious in silhouette. That thinness is not just aesthetic, it is a dynamical constraint on temperature, turbulence, and vertical gravity. But a rotating disk is not a solid record, and it does not behave like a rigid wheel. It is differentially rotating, meaning inner orbits complete faster than outer ones, and the difference is large. In M51, material near the centre circles in tens of millions of years, while the outer disk takes a few hundred million. Differential rotation creates shear that stretches any fixed feature over time, pulling it into a tighter and tighter wrap. This creates the winding problem, which is simple to state and hard to escape. If spiral arms were made of the same stars and gas permanently, shear would wrap them into a tight coil in only a few rotations. The whirlpool would lose its open, grand design quickly on galactic timescales, becoming a smeared ring rather than a readable spiral. The fact that we see long-lived spiral patterns means the arms cannot be purely material structures. The winding problem was one of the conceptual pivots in galactic astronomy, because it forced a move from static pictures to dynamical thinking. It asked a blunt question: are we seeing a permanent structure, or a pattern that can persist while matter flows through it? That question becomes more urgent in a galaxy like M51, where the arms are unusually crisp and continuous. The arms look carved, yet the disk is in constant motion. To understand the disk's motion, we need one more layer of dynamics, because orbits in a galaxy are not perfect circles. Even when the disk looks smooth, stars and gas execute small oscillations around their guiding centers, called epicyclic motion. These oscillations arise because gravity and rotation do not balance perfectly at every instant, especially in a non-uniform potential. The epicycles matter because they set resonances and determine how waves propagate through the disk. An epicycle is easier to picture as a gentle wobble superimposed on an overall orbit. A star's guiding center moves around the galaxy, while the star itself oscillates radially and azimuthally around that center. The frequency of that oscillation depends on the mass distribution, so it becomes a diagnostic of the potential. In plain language, the way stars wobble tells you how gravity is shaped. Differential rotation and epicycles together define the disk's response to perturbations, and they determine whether disturbances fade or organize. A disturbance can be stretched by shear, but it can also be gathered into a wave pattern that has its own coherence. The key idea is that the spiral can be a pattern speed, not a set of permanent particles. Matter flows through the pattern, compressing and rarefying as it goes, like water passing through a standing wave. Spiral density wave theory frames the arms as long-lived regions of enhanced density, maintained by the disk's collective gravity. The wave rotates with its own angular rate, which can differ from the local orbital rate of stars and gas. Stars and gas enter the arm, slow slightly in the potential trough, and then exit, continuing their orbits. The arm persists because it is continually reinforced by the disk's response, rather than carried as a fixed ribbon of matter. In this view, the arm is like a traffic jam in orbit, and the analogy is useful because it separates pattern from participants. Individual cars change, but the jam pattern remains, shaped by constraints and feedback. Gas is especially sensitive because it can collide, shock, and lose energy, unlike stars that mostly pass through each other. Where the wave compresses gas, clouds become denser and more likely to collapse. Compression is not uniform across the arm, and that unevenness is part of what makes the arms visually rich. Gas can experience streaming motions, moving along and across the arm relative to circular rotation, and those motions can be tens of kilometers per second. These non-circular motions are measurable in velocity maps, appearing as systematic deviations from a simple rotating disk. They reveal where gravity is pulling gas into the arm, and where shocks are dissipating energy. When we imagine a spiral shock, we should not picture a single sharp front like a wall. In reality, it is a region where gas piles up, turbulence rises, and magnetic fields can be stretched and amplified. The gas may heat as it compresses, then cool by radiating in infrared and millimeter wavelengths, leaving it denser than before. That cycle changes chemistry as well, because molecules form more readily in shielded, dense regions. Observationally, different traces reveal different layers of the same dynamics, and the comparison is where the story becomes three-dimensional. Neutral hydrogen, Hi, maps the diffuse outer reservoir and the extended disk, often reaching beyond the optical boundary. Molecular gas traced by CO maps, denser clouds that are closer to star formation, concentrated along the arms. Optical emission lines trace ionized gas around young stars, which marks where collapse has already happened and massive stars have turned on. Each tracer carries its own biases, and learning those biases is part of the science. HI is abundant but diffuse, so it highlights large-scale structure and tidal distortions in the outskirts. CO is a proxy because molecular hydrogen is hard to see directly, so astronomers use CO brightness to estimate molecular mass with calibrated conversion factors. Ionized gas, glowing in lines like H-alpha, is bright but short-lived as a tracer because it depends on massive stars that quickly die. When astronomers compare these tracers, they see offsets along the arms, and those offsets function like timestamps. Dust lanes and molecular gas often lead the brightest young clusters, consistent with a shock that compresses gas first. Then star formation ignites downstream as clouds collapse and massive stars turn on, lighting the surrounding gas. The pattern provides a clock that links dynamics to stellar ages, turning geometry into chronology. In M51, those offsets can be subtle in a single image, but they become obvious in layered maps. A dark dust lane hugs the inner edge of an arm, then a ridge of CO follows, and then blue star clusters appear slightly farther along. It is as if the arm contains a conveyor belt of phases: diffuse gas, compressed gas, newborn stars, and then dispersal. The arm is not merely a decoration, it is a sequence of physical states. The density wave picture is not the only mechanism, and real galaxies mix processes in ways that depend on environment. Spiral structure can be transient, recurrent, and driven by multiple triggers, including self-gravity, swing amplification, and external forcing. In M51, the companion NGC 5195 is not a minor detail but a major driver, sitting close enough to tug the disk out of symmetry. Its gravity can amplify a spiral pattern, strengthen shocks, and reorganize angular momentum. Tidal interaction acts through differential gravity across the disk, and the word tidal is literal in the same way it is for oceans. The near side of M51 feels a stronger pull than the far side, creating a torque that distorts orbits. That torque can draw out bridges and tails, and it can drive waves inward that steepen into stronger arms. It can also concentrate gas by crowding orbits, raising density where the disk is already marginally stable. The bridge between M51 and NGC 5195 is evidence of that exchange, and it is also a reminder that galaxies are not isolated islands. Material is pulled outward and redistributed, not destroyed, and the process is surprisingly graceful at large scales. Tails and streams store orbital energy and angular momentum in extended structures, faint but dynamically important. Over hundreds of millions of years, some of that material can fall back, feeding the disk and reshaping the arms again. If we could watch the interaction in accelerated time, the scene would look less like a collision and more like a slow dance. The companion passes, the disk ripples, and the arms respond like a disturbed fluid settling into new modes. The outer gas stretches into arcs that fade into intergalactic space, while the inner disk tightens and brightens. The galaxy's present appearance is one frame in a long sequence of gravitational cause and effect. Interactions are common in cosmology, not rare accidents, and they are built into the hierarchical growth of structure. Galaxies grow by accreting smaller systems, and by repeated close passes, and each encounter leaves dynamical fingerprints. Encounters can trigger bursts of star formation, thicken disks, and move gas inward towards central regions. M51 is a nearby example of a process that has shaped galaxies across cosmic time. The companion's pull also helps explain why M51's arms are unusually crisp, because a strong perturbation can favour a dominant two-armed mode. A tidal disturbance can seed a strong M+2 pattern, reinforcing a grand design spiral rather than many flocculent fragments. The disk responds as a self-gravitating fluid of stars and gas, supporting waves that would be weaker in isolation. The result is a pattern that looks stable even while it is continually driven. Yet even a driven pattern must contend with the disk's internal limits, because a disk cannot form stars everywhere at once. It must balance gravity against pressure, turbulence, magnetic support, and shear, and that balance varies with radius. This competition is often summarized by the Toomre Q parameter, which acts like a clumpiness gauge for gravitational instability. When Q is high, the disk resists collapse and remains relatively smooth, but when Q drops near unity, the disk becomes unstable and fragments. We do not need the full equation to use the intuition, but we do need to respect what Q measures. Q rises when velocity dispersion is high, when gas is warm or turbulent, and when shear is strong, because those effects oppose self-gravity. Q falls when surface density is high, when gas is cold, and when rotation provides less stabilizing support. Spiral arms and tidal forces can locally lower Q by increasing density and by enhancing cooling efficiency in compressed gas. This is why the arms are not just brighter, they are more precarious, perched closer to collapse. In the interarm regions, gas may be too diffuse or too stirred to fragment, so it drifts in a more stable state. In the arms, orbits crowd and shocks form, and the same gas crosses a threshold into bound structures. The galaxy's star formation becomes spatially organized by the dynamics that shape the spiral. Cold gas is the key because it can radiate energy away, and radiation is how the gas sheds pressure support. When gas cools, thermal pressure weakens and gravity wins more easily, allowing density to rise further. In a spiral shock, gas is compressed, heated briefly, and then cools again, ending denser than before. That cycle can push regions over the instability threshold, producing giant molecular clouds and star-forming complexes. Giant molecular clouds are not small objects on galactic scales, and in M51 they can reach tens of parsecs across. Within them, turbulence and gravity compete, and only the densest pockets collapse into clusters. The rest of the cloud may be shredded or dispersed by feedback before it can form many stars. Even so, the clouds represent a temporary concentration of mass, created by the arm's dynamics and erased by the next phase. This is how gravity becomes light without magic, and the sequence is physically grounded. The arm concentrates gas, the gas collapses into stars, and the stars illuminate the arm, making the wave visible. Yet the brightest stars live briefly, often only a few million years, because massive stars burn fuel quickly. Their short lifetimes mean that luminous knots trace recent conditions, not long-term averages. Timescales keep the story honest, because they prevent us from confusing a snapshot with a permanent structure. An orbital period in the inner disk can be tens of millions of years, while the outer disk can take a few 100 million. Massive stars die before a full orbit in many regions, so their positions mark where gas was compressed recently. The spiral pattern can persist across many orbits, but the luminous traces are constantly replaced. This makes spiral structure both transient and self-renewing, a paradox that becomes intuitive once pattern and matter are separated. Individual star-forming regions flare and fade quickly, and their clusters drift away from their birth sites. Gas clouds are assembled, disrupted by feedback, and reassembled elsewhere, sometimes within the same arm. The arm pattern can remain coherent while its contents turn over repeatedly. Feedback complicates the clean picture of collapse, because star formation is not a one-way conversion of gas into stars. Young stars emit ultraviolet radiation that ionizes gas and heats dust, carving cavities and bright rims. Stellar winds and supernovae inject momentum and turbulence, raising Q and resisting further collapse locally. Feedback can also compress neighboring gas, triggering secondary star formation along the arm, so suppression and stimulation coexist. In images, feedback appears as bubbles, filaments, and glowing shells, and those shapes are the geometry of energy injection. Ionized regions expand into surrounding material, and shock fronts sweep up gas into arcs. Some of that swept gas becomes dense enough to collapse, while other portions are dispersed into the interarm medium. The arm becomes a workshop of competing processes, with gravity building and feedback dismantling. The net effect is regulation rather than simple consumption, and regulation is essential for a galaxy's longevity. A galaxy that turned all its gas into stars quickly would burn out early, leaving a red, quiet remnant. M51 appears to operate in a controlled regime, where inflow, compression, and feedback maintain a steady conversion rate over long times. The interaction can push the system toward higher activity, but it does not erase the need for balance. Dark matter remains present in every step, even when we focus on the disk's visible drama. The halo sets the overall rotation curve, which sets the shear profile, which influences stability and wave propagation. It also affects how strongly the disk self-gravitates, which changes how easily spiral modes grow and persist. A heavier halo can stabilize against bar formation, while still allowing spiral patterns, depending on disk mass and temperature. Rotation curves therefore do more than prove dark matter, because they constrain how mass is distributed between bulge, disk, and halo. They tell us how much of the gravitational field comes from luminous matter, and how much from the unseen component. In practice, astronomers fit models that combine stellar mass-to-light ratios with gas distributions and a halo profile. In M51, the flat curve implies that the visible spiral is embedded in a much larger, darker structure. There is also a subtle point hidden in the curve's shape, because not all flat curves are identical. The inner rise reflects the bulge and inner disk, where luminous matter can dominate locally. The outer plateau reflects the halo's growing contribution, smoothing the potential and keeping speeds high. The curve is therefore a fingerprint of how different components share the gravitational load. Velocity fields add another layer of evidence, because they show where the disk deviates from simple circular motion. If gas moved on perfect circular orbits, the Doppler map would be smooth and symmetric, with clean contours. In M51, deviations from circular motion appear along the arms and near the interaction region, bending the contours. These streaming motions are signatures of spiral shocks, tidal forcing, and the response of gas to a non-axis symmetric potential. HI kinematics reveal the outer disk's response to the companion, and the outer disk is often where tidal effects are easiest to see. The diffuse gas shows warps, asymmetries and extended features that trace tidal stripping and compression, sometimes forming lopsided structures. CO kinematics reveal denser gas flowing along the arms and piling up near dust lanes, where shocks are stronger. Together they show that the arms are not just bright regions but dynamical features that redirect mass. In a well-resolved velocity map, the arms can be read like currents in a river. Gas approaches the arm, slows and compresses, then accelerates away, leaving a systematic pattern of residual velocities. Those residuals are not noise because they repeat along the spiral and correlate with dust lanes and star formation. The galaxy is telling us in numbers where it is being squeezed. These measurements also help locate resonances, which are the special radii where orbital and pattern frequencies line up. Where the pattern speed matches the orbital speed, at corrotation, gas and stars linger relative to the wave, and the character of shocks can change. Inside corrotation, material overtakes the pattern, and shocks can be strong along the leading edges of arms. Outside corrotation, the pattern overtakes the material, and the geometry of offsets shifts accordingly. Resonances can organize rings, gaps, and changes in star formation efficiency, even when the galaxy does not display obvious rings. They also matter for angular momentum exchange, because waves can transport angular momentum outward. That transport can slowly rearrange the disk, moving gas inward and altering surface density profiles. The spiral is therefore not only a pattern we see, but a mechanism that can reshape the galaxy over time. The Whirlpool's elegance is therefore a balance between competing motions, and the balance is delicate. Gravity pulls inward while angular momentum resists, and the compromise is rotation. Shear stretches features while collective gravity gathers them into waves, and the outcome depends on temperature and mass. Cooling allows gas to collapse while feedback reheats and stirs it, preventing runaway consumption. The companion perturbs the disk while the halo provides a stabilizing background potential. This balance is not static, and it is not guaranteed to persist unchanged across cosmic time. Over hundreds of millions of years, repeated tidal forcing can rearrange the disk's angular momentum and thicken parts of the disk. Gas can be driven inward, building central concentrations and changing the inner potential, which then changes orbital structure. The same processes that sharpen arms can also prepare conditions for central activity later in the story. Historical context matters because these ideas were not obvious, even to careful observers with excellent telescopes. Early astronomers saw spirals and assumed they were material structures, like pinwheels frozen in place. The winding problem forced a shift from purely geometric descriptions to dynamical explanations, and it demanded a mechanism for persistence. Rotation curves then forced a second shift, from luminous mass to invisible mass as a dominant component. M51 sits at the intersection of those revolutions, which is part of why it remains a teaching galaxy. It is a textbook spiral that also exposes the limits of textbook thinking, because it is shaped by both internal dynamics and an external companion. Its arms are too organized to be random, too persistent to be simple material traces, and too fast in the outskirts to be held by starlight alone. The galaxy's beauty becomes a diagnostic, pointing to hidden mass and collective behavior. We can now restate the central question with sharper edges, because we have replaced appearance with mechanism. What physical processes, visible and hidden, build and sustain the Whirlpool's spiral structure? How do dark matter, orbital dynamics, and tidal forcing cooperate to shape the disk. How does that structure then control where gas collapses, where stars form, and where energy is injected back into the system? The answer begins with a blueprint that cannot be photographed, because it is written in gravity rather than light. The halo's gravity sets the rotation curve and the disk's stability regime, and it defines the background in which everything else unfolds. Differential rotation and epicyclic motion define how patterns can exist without winding up, even in a shearing disk. Density waves and tidal forcing provide the organizing framework that keeps the spiral readable across time. From the halo down to the disk, the story is one of guided flow, where matter responds to an invisible architecture. Matter follows the potential, and the potential is dominated by the unseen, especially in the outskirts where the curve stays flat. Gas responds by cooling, shocking, and collapsing where the pattern compresses it, and then by being dispersed again. Stars respond by tracing the wave briefly, then drifting onward as the pattern persists. To understand it, we cannot rely on one kind of light. We need Doppler maps, HI and CO surveys, and stellar tracers that mark different phases of the cycle. We need to connect kinematics to mass, and mass to stability, and stability to star formation, because each link constrains the next. Only then does the spiral stop being a picture and become a process. The chapter ends with a shift in emphasis. Gravity explains why the whirlpool holds together and why its arms can persist, even under shear and disturbance. The next question is how the pattern becomes luminous, and why the arms are crowded with short-lived beacons. We move from blueprint to production, entering the arms as star factories where gas becomes suns. We leave the abstract blueprint of gravity and enter the arms where matter changes state. The whirlpool spiral is not only a wave in orbits, because it is also a conveyor of gas, dust, heat, and chemistry. In these lanes, material cycles through phases that decide what becomes a star, what remains diffuse, and what gets blown apart. The arm is a riverbed in motion. Its banks are drawn by gravity, while its water is made of atoms, molecules, and charged plasma. From a distance, M51 looks like a calm pinwheel painted in blue and gold. Up close, each arm is a moving boundary layer, an interface where cold clouds, warm atomic gas, and hot ionized plasma exchange energy. The pattern seems fixed, yet the substance inside it is always in transit. Even the starlight is part of the flow, because radiation pushes, heats, and breaks molecules apart. The interstellar medium is not a uniform fog. It is a layered ecosystem where temperature, density, and radiation set distinct regimes, and those regimes can coexist within the same line of sight. In one region, hydrogen is molecular and cold, in another it is atomic and diffuse, and in another it is ionized and glowing. The boundaries are not clean walls. Turbulence and radiation blur them into gradients, like weather fronts folding into one another. This is not just a classification scheme for astronomers. Each phase has different sound speeds, different cooling pathways, and different responses to pressure, which means each phase moves and collapses differently. The arms are where these differences become visible as offsets, filaments, bubbles, and luminous knots. When we watch the arm in multiple wavelengths, we are watching the same material change its rules while it keeps moving. The coldest layer is molecular gas, mostly H2, packed into clouds that can hide from starlight. In the densest pockets, temperatures can drop to only a few tens of Kelvin, so thermal motions slow and gravity gains leverage. Molecular hydrogen is abundant, yet it is hard to detect directly at these temperatures because it radiates weakly. Its symmetric molecule has no strong dipole emission in the cold, so it keeps its presence quiet, like a reservoir with no surface ripples. So observers track carbon monoxide as a practical tracer, even though CO is only a minor constituent. CO's rotational transitions emit at millimeter wavelengths, and those photons slip through dust that would block visible light. By mapping CO brightness and velocity, astronomers infer where the fuel is concentrated and where collapse is most likely. The conversion from CO light to H2 mass is not perfect, because it depends on metallicity and shielding, yet it remains one of the clearest ways to weigh invisible cold gas. The maps are more than pictures. They are kinematic diagrams of a galaxy's breathing. A CO spectrum is split into Doppler-shifted components, revealing streaming motions as gas enters an arm and then drifts downstream. In M51, these velocity patterns align with the spiral geometry, turning the arm into a measurable flow field. The line widths also carry a second message. Turbulence and cloud-to-cloud motions broaden the signal, hinting at how violently the gas is being stirred. Around that molecular layer lies atomic hydrogen, HI, more extended and less shielded. HI emits the 21 centimeter line, a hyperfine transition that radio telescopes can detect across enormous distances. This line is faint per atom, yet the sheer mass of HI makes the disk glow in radio maps. The physics is subtle and elegant. An electron flips its spin relative to the proton, releasing a photon with a wavelength long enough to pass through dust almost untouched. HI shows where the galaxy stores raw material before it is assembled into denser clouds. It also marks the boundaries where ultraviolet light can penetrate, dissociating molecules and keeping gas in a warmer, more diffuse state. In the interarm regions, HI can dominate, like a broad river feeding narrower molecular tributaries. In those quieter lanes between arms, the gas can cool and gather slowly, waiting for the next spiral passage to compress it again. Where massive young stars appear, hydrogen becomes ionized and forms HOCI regions. These zones glow in optical emission lines and in radio free emission, marking the presence of ultraviolet radiation. The light is not continuous like a lamp, because it is produced by electrons recombining with protons and cascading through energy levels. Each bright line is a fingerprint of quantized physics, and each glowing nebula is a sign that a few very hot stars are spending their short lives at full intensity. HI regions are brief signposts because they require short-lived massive stars to keep them lit. Their edges are often sharp, where ionization fronts meet neutral gas and create bright rims. In images, these nebulae look like lanterns hung along the arm, but each lantern is a pressure-driven expansion. The glow is beautiful, yet it is also a warning that the surrounding molecular cloud is being eroded from the inside out. Dust threads through every phase, even when it is only a small fraction of the mass. Dust grains absorb ultraviolet and optical light and re-radiate it in infrared, turning hidden structure into thermal emission. In the coldest clouds, dust becomes a quiet thermometer because its glow tracks the energy absorbed from starlight. Grain temperatures shift by only a few degrees, yet those shifts encode whether a region is sheltered, heated, or newly exposed. Dust both blocks and reveals, because extinction outlines dense lanes while infrared glow marks where energy is being deposited. In optical images, dust lanes look like ink strokes across the spiral, cutting through star fields with sudden darkness. In infrared, those same lanes can brighten, as warmed grains whisper their presence rather than conceal it. The same material that steals visible photons returns them at longer wavelengths, so the galaxy changes personality as the camera changes colour. The grains themselves are small, yet their effects are large. By providing surfaces where atoms can meet, dust helps form H2 efficiently, which is otherwise difficult in the tenuous gas. Dust also shields molecules from destructive ultraviolet photons, so chemistry can proceed in the dark. On those grain surfaces, simple reactions build more complex species, turning a cold cloud into a chemical workshop that is invisible to the eye. This layered medium is the real subject of the arms. Stars are the visible outcome, but gas and dust are the working substance, and their transitions set the tempo. To follow the Whirlpool's life cycle, we track matter as it flows between phases and across thresholds. The arm is therefore not just a place, but a sequence, an ordered procession of conditions that repeats as long as the disk keeps rotating. Spiral arms organize that flow by forcing gas through a changing gravitational environment. As gas approaches an arm, orbits crowd and streaming motions develop relative to circular rotation, so material converges. The crowding steepens into a spiral shock front, a region where gas is compressed and turbulence rises. In a strong spiral like M51, the shock can be coherent over thousands of light years, even though the clouds inside it remain fragmented and irregular. A shock in a galaxy is not like a solid wall, yet it behaves like a traffic jam. Gas parcels catch up to slower moving material, kinetic energy is dissipated, and pressure spikes in a narrow zone. Cooling then determines what happens next, whether the gas rebounds, fragments, or settles into a denser ridge. If cooling is efficient, the compressed layer can become thin and unstable, breaking into clumps that seed the next stage of collapse. The upstream signature of that compression is often a dust lane. dust concentrates where gas density increases and where cooling becomes efficient, so the lane appears before the brightest star-forming knots. In M51, this offset is measurable, and it is a physical timeline rather than a photographic coincidence. It is also a reminder that the arm is not a string of independent fireworks, because the fireworks have a shared upstream cause. Visually, the lane is a dark seam stitched along the inner edge of the arm. It is not empty space, but a curtain of grains and cold gas that absorbs background starlight. When the camera shifts to longer wavelengths, the seam becomes a ridge, and the ridge becomes a reservoir. In a slow pan across the arm, the dust lane feels like a shadow with depth, as if the galaxy has folds and creases rather than a flat painted surface. Downstream from the dust lane, bright clusters and He regions appear. The separation between lane and glow acts like a time delay clock, set by collapse times and orbital speeds. Geometry becomes chronology, because the arm carries gas forward while gravity works inward. The sequence is readable. First the dark compression ridge, then embedded infrared warmth, then exposed blue clusters that have cleared their immediate surroundings. That clock can be read in degrees around the spiral, which translate into millions of years. If the gas rotates past the arm at a known speed, the angular offset becomes a delay between compression and ignition. In M51, the offsets are large enough to show that star formation is not instantaneous. Even in a strong spiral, the arm gives the gas a push, but the gas still needs time to cool, fragment, and assemble dense cores. The shock does not guarantee star formation. It raises density, but collapse still depends on whether gravity can defeat internal support, and that support is multi-layered. The central question tightens here, because the Whirlpool's beauty hides a regulatory system that prevents runaway conversion of gas into stars. The arm sets the stage, yet the actors, pressure, turbulence, and magnetic fields, still decide whether the scene becomes a birth or a near miss. Cloud physics can be stated without equations, but the competition is exacting. Gravity pulls inward, thermal pressure pushes outward, and turbulence adds chaotic motion that can mimic pressure support. A cloud collapses when self-gravity wins over these supports on a given scale. The key is scale, because a cloud can be stable as a whole while still forming stars in its densest pockets. Thermal pressure is the simplest to imagine, because it is tied to temperature. Warm gas has faster particles, so it resists compression more strongly than cold gas. Cooling therefore matters not as a detail, but as a lever that changes how easily a region can be squeezed. In molecular gas, cooling often comes from CO and other molecules, while at higher densities dust emission takes over, carrying energy away in infrared. The genes idea captures the threshold. For a given temperature and density, there is a characteristic mass and size above which a region becomes unstable. Cooling lowers pressure and shrinks the threshold, so cold dense pockets are the easiest places for gravity to take control. In plain language, cold gas is easier to gather because it does not fight back as hard when gravity tightens. Historically, this way of thinking grew from early 20th century attempts to understand why stars form at all. Genes framed collapse as an instability in a self-gravitating medium, and later work added realism through rotation, turbulence, and magnetic fields. The modern picture keeps the same core insight. Collapse is conditional, not automatic. That insight matters in a spiral arm, because the arm's compression is powerful, yet it still must negotiate these conditions. Turbulence complicates the picture because it plays two roles at once. On large scales, it can support a cloud by stirring it and raising effective pressure, which delays global collapse. On smaller scales, it creates shocks and filaments that locally increase density, seeding collapse inside an otherwise supported cloud. This is why a cloud can look chaotic and still be productive, because disorder can create the very pockets where gravity wins. In images of molecular clouds, those filaments look like braided ropes. They intersect, merge, and sometimes end in bright cores, as if the cloud is tying knots in itself. The knots are not decorative because they are where the density peaks, and the freefall time becomes short. Along an arm, those filaments can align with shear and magnetic fields, giving the cloud a grain, like wood shaped by a current. Magnetic fields add a third competitor, threading clouds and coupling gas to charged particles and dust. Fields can resist compression across field lines and slow the drift of material into dense cores. They can also guide flows along preferred directions, shaping filaments and influencing where collapse concentrates. Observationally, polarization of dust emission can trace this hidden architecture, revealing an order that optical images cannot show. Even a weak field can matter, because interstellar gas is often partially ionized. Charged particles spiral along field lines, and through collisions they tug on neutral atoms, making the whole mixture less free to move. The result is a kind of frictional delay. Collapse can proceed, but it must negotiate the field. That delay is part of the reason star formation proceeds in fits and starts, rather than as a single, smooth implosion. These supports help explain why star formation is inefficient. Most molecular gas does not turn into stars in a single freefall time, even in active spirals. Clouds are disrupted, stirred, and recycled, so only a small fraction reaches the densities required for sustained collapse. The inefficiency is not a flaw, because it keeps the galaxy from burning its fuel in one brief blaze. There is an observational way to feel that inefficiency. If all the molecular gas in M51 collapsed quickly, the galaxy would blaze far brighter, and then fade, because it would run out of fuel. Instead, the arms maintain star formation over long spans, implying regulation rather than a one-time burst. The steady presence of both gas and young clusters suggests a balance between assembly and dispersal that repeats for billions of years. In M51, the inefficiency is not a failure of the process. It is the mechanism that keeps the galaxy alive for billions of years, sustaining a steady conversion rather than a sudden purge. A disk that converted gas too efficiently would exhaust itself quickly and lose the blue, luminous character of its arms. The Whirlpool's elegance is therefore partly restraint. Its brightest regions are intense, but they are also carefully rationed by physics. Within a molecular cloud, the path to a star begins in dense cores. A core forms where density peaks, and cooling is strong enough for gravity to tighten its grip. As the core contracts, it heats, but it can still radiate away energy through dust and molecular lines. The collapse accelerates as density rises, because the freefall time shortens, and the core becomes a countdown toward ignition. The ability to radiate is crucial, because collapse generates heat. If the heat stayed trapped, pressure would rise and halt infall, so cooling is the escape valve that lets gravity keep working. In the densest regions, dust emission becomes a dominant channel, carrying energy outward in infrared. That infrared glow is faint on human scales, yet across a galaxy it marks the hidden places where stars are actively assembling. Collapse is never perfectly radial because the cloud inherits angular momentum from galactic rotation and turbulence. As material falls inward, it spins faster, and centrifugal support builds in the equatorial plane. The result is an accretion disk, a structure that stores angular momentum while feeding mass onto the growing protostar. In this way, the galaxy's rotation leaves a signature on a system that is only a few astronomical units across. Disks are not just byproducts, they are the reason planets can exist later. By flattening material into a rotating plane, a disk creates a long-lived environment where solids can grow and migrate. Even before planets, the disk is a mechanical translator between a cloud measured in light years and a star measured in solar radii. It is also a chemical reactor because temperature gradients and radiation fields sort molecules into distinct zones. The protostar is not yet a normal star. It shines mainly from gravitational energy released by infall and accretion, not from sustained hydrogen fusion. Its luminosity and temperature evolve as mass accumulates and the interior becomes hot and dense enough for nuclear reactions. The moment fusion stabilizes the core is a threshold, yet the surrounding disk and envelope can persist, continuing to shape what the system becomes. In this phase, the object is wrapped in dust and gas, so much of its light is reprocessed. The protostar's energy warms nearby grains, and the grains re-radiate in infrared, making the cradle glow even when the star itself is invisible. What looks like darkness in optical can be a warm, structured landscape in the infrared. The arm's hidden nurseries are therefore not empty, because they are crowded with faint forming suns. Accretion is not smooth. Gas spirals through the disk, losing angular momentum through turbulence, magnetic stresses, and disk instabilities. The disk becomes the mediator between a large cloud and a small star, translating galactic scale flows into stellar scale growth. In that translation, a great deal of energy is released, and that energy begins to reshape the immediate environment long before the star is fully mature. Those instabilities can create bursts, where the accretion rate jumps and the protostar brightens. In a galaxy-wide context, such variability is microscopic, yet it changes how feedback begins. A brighter protostar heats its surroundings more strongly, which can alter the chemistry and the fragmentation of nearby gas. Even small changes in heating can decide whether a neighbouring clump becomes another star or disperses back into the cloud. Jets and outflows emerge early and are not decorative side effects. Magnetic fields anchored in the disk can launch collimated jets that carry away angular momentum. By removing angular momentum and injecting momentum into the surrounding cloud, jets help regulate how fast the protostar can grow. They also punch holes through the envelope, creating escape routes for radiation that would otherwise be trapped. Visually, jets are like needles of motion, piercing the cocoon and marking the rotation axis. Where they slam into surrounding gas, they can create shock-excited knots and bow shapes, which glow in specific emission lines. These structures are small compared to spiral arms, yet they echo the same theme: flow, compression, and release. The arm's grand pattern is mirrored in miniature, as if the galaxy repeats its logic at every scale. Outflows also carve channels through the natal material, changing how radiation escapes. They can reduce the choking effect of infill and allow the system to evolve toward visibility. They also stir the cloud, feeding turbulence back into the environment that is trying to collapse. This is one of the cycle's quiet ironies, because formation injects disorder into the gas that must become orderly to fall inward. This birth sequence is a chain of states that different wavelengths can isolate. Optical light highlights exposed clusters and ionized gas where massive stars have already cleared their surroundings. Infrared penetrates dust and reveals embedded protostars and warm dust heated by early activity. Millimeter and radio wavelengths trace the cold reservoirs, where the story begins long before the first blue light appears. In optical images, the arm's brightest knots look crisp and almost decorative, yet their sharpness is a sign of excavation, because the cluster has cleared dust that would otherwise soften the view. The blue light is a clue that massive stars are present, and that their clocks are already running. If we linger on those clusters, we can almost sense the imbalance, because the brightest stars are the most short-lived. Infrared views change the mood. The arm becomes a set of glowing embers embedded in darker lanes, with warm dust tracing ridges that optical light cannot cross. What appears empty in visible light can be crowded with forming stars, each wrapped in its own envelope. In this view, the spiral is less a pinwheel and more a braided current, with heat tracing where gravity has recently tightened. Radio and millimeter observations trace the coldest stages. CO maps the molecular reservoirs and the dense ridges shaped by spiral shocks. Longer radio wavelengths trace HI in the outer and interarm regions, showing where gas is stored before it becomes molecular. Together, these maps show that the galaxy is not made of stars alone, because much of its mass and future is still in gas. These data also reveal motion, because line profiles encode velocity. A single pointing can show multiple components along the line of sight, hinting at overlapping structures and streaming flows. In M51, the arm's kinematics show that gas does not simply orbit, but continually accelerates and decelerates through the spiral potential. The spiral pattern is therefore not merely a picture, because it is a dynamical machine that reshapes trajectories. These observational anchors are not separate stories, they are slices through one cycle, and the cycle is what the arms enforce. When we layer the wavelengths, we see a progression from diffuse gas to compressed dust lanes, to embedded sources to exposed clusters. The sequence is not perfectly orderly, yet the offsets and correlations are strong enough to read like a physical script. The layering can be made literal in a composite image, where radio contours sit atop infrared glow and optical clusters. The eye then follows a sequence along the arm as if reading a sentence written in different colours. The galaxy becomes a timeline you can point to. It invites a question that is both simple and unsettling. How much of what we call structure is really just a snapshot of material passing through stages? The calm mystery of the arms comes from their scale. Across thousands of light years, the pattern looks steady and graceful, as if it were carved in place. But locally, every bright nebula is an unstable, short-lived phase, and its existence implies that a collapse has already begun to erase its own birthplace. The arm persists as a pattern, while its contents are replaced like water in a river that keeps the same bends. That erasure is not metaphorical. As soon as massive stars ignite, they change the pressure balance, the chemistry, and the opacity of their surroundings. The very light that makes the region visible also begins to dismantle the cloud that fed it. In the brightest knots, the clearing happens quickly enough that we can infer the timing from what remains: pillars, rims, and shredded dust lanes. Massive stars accelerate that erasure. They form less often than low-mass stars, but they dominate feedback and radiation. Their ultraviolet light ionizes surrounding gas, creating expanding HE regions that push against the molecular cloud. In a spiral arm, where many stars form in clusters, these expanding regions can overlap, turning isolated bubbles into connected cavities. Ionization is a phase change with consequences. Neutral gas becomes plasma, its temperature jumps to around 10,000 Kelvin, and its pressure rises sharply. That pressure drives expansion, so an HI region is not static illumination, but a moving front. The front can be ragged and sculpted, because it advances faster through low-density gaps and stalls against dense clumps. As ionized gas expands, it drives shock fronts into the surrounding medium. It can compress nearby material into dense shells that may fragment and collapse, triggering secondary star formation. It can also disperse gas and halt accretion, quenching growth in the immediate region. The same feedback can therefore either propagate the cycle or cut it short, depending on where the pressure finds an escape. This dual outcome depends on timing and geometry. If a shell gathers mass faster than it leaks, it can become gravitationally unstable and break into clumps. If the region vents into lower density space, the pressure drops and the cloud can be shredded instead. The arm's environment matters here, because spiral shocks and shear can confine gas in some places while opening corridors in others. Stellar winds add momentum and heat, carving cavities and stirring turbulence. Winds can combine with radiation to evacuate bubbles that merge into larger superbubbles in clustered environments. In the arms of M51, these processes can propagate along the spiral, linking one generation to the next. The arm becomes a corridor where feedback travels, because dense gas and young clusters are strung along the same route. In images, wind-blown cavities appear as arcs and hollowed interiors, with bright rims where gas piles up. The rims are often where dust survives longest, outlining the bubble like smoke around a flame. The arm's structure is therefore not only lanes and knots, but also shells and voids. If we could hear the arm, it would not be silent, because expansion and shocks would be its percussion. Supernovae arrive quickly for the most massive stars, on timescales of only a few million years. The explosion injects energy into the interstellar medium and drives hot plasma that can shine in X-rays. Supernova remnants sweep up gas, mix heavy elements, and can either compress clouds or shred them. The blast waves are brief, yet their cumulative effect is long-lived, because they maintain turbulence and heat in the diffuse phases. A supernova is a point event with galaxy-scale implications, because it seeds turbulence and heats diffuse gas. The remnant expands, cools, and eventually merges back into the medium, leaving behind altered chemistry and altered structure. In a spiral arm, many such events overlap in time, building a background of agitation. The arm's glow is therefore partly a record of recent deaths, even when we are focused on birth. Feedback therefore has two faces. It is destructive because it disperses clouds and ends the embedded phase. It is creative because it can compress new regions and seed collapse, especially where the arm already keeps gas near the instability threshold. This is one reason spiral arms can look like chains of pearls, because bright regions can influence their neighbours without controlling them completely. This is one reason spiral arms can look like chains of pearls. A bright region can trigger a neighbour, and that neighbour can trigger another, but always with delays set by expansion speeds and cooling times. The arm becomes a sequence of cause and consequence, written in gas dynamics. The spiral arm becomes a chain reaction with delays, where the initial compression sets conditions and later feedback edits the outcome. There is a subtle question beneath this choreography. Is the arm merely organising star formation that would happen anyway, or is it actively increasing the rate by pushing gas over thresholds? In M51, the strong, well-defined lanes suggest the arm is doing more than decorating the disk. The offsets, shocks, and coherent dust ridges imply that the spiral pattern is an active participant, not a passive backdrop. Chemical enrichment is the quiet continuity beneath these bursts. Each generation of stars returns processed material through winds and supernova ejecta. Over time, the gas gains heavier elements, and dust grains grow more abundant and more complex. The arm is therefore not only moving matter because it is upgrading it, adding new coolants, new solids, and new chemical possibilities. This enrichment is slow compared to the life of a single nebula, yet it accumulates relentlessly. The first generations of stars in the universe formed in a simpler medium, with fewer coolants and less dust. Galaxies like M51 are later chapters, where many cycles have already thickened the chemical palette. When we see dust lanes and rich molecular emission, we are seeing the legacy of countless earlier stars. Metallicity matters because it changes cooling. Heavy elements provide additional line emission, letting gas radiate energy away more efficiently and reach lower temperatures. More dust also improves shielding from ultraviolet radiation, allowing molecules to survive and clouds to remain cold. In plain terms, metals make it easier for gas to lose heat, and cold gas is easier to compress. That means enrichment can alter the efficiency of future star formation, not by changing gravity, but by changing the thermodynamics. The arms are therefore both consumers and engineers of their own fuel. They compress gas into clouds, then return metals and dust that make the next round of cooling more effective. The cycle is self-modifying, which is one reason galaxies evolve rather than simply repeat. Metallicity also matters for what comes after star formation. Dust and heavy elements are the ingredients for rocky planets, complex chemistry, and the solid cores that can build giant planets. The arms are therefore not only making stars, they're preparing the raw material for future planetary systems. Even in this chapter's focus on birth, the implication is unavoidable, because the same dust that hides protostars later becomes minerals, oceans, and atmospheres. In M51, we can read enrichment indirectly through colours, emission lines, and dust content. Regions with strong recent star formation show signatures of ionization and heating, while older regions show different spectral balances. The galaxy's disk becomes a map of both present activity and accumulated history. Emission line ratios can hint at temperature and composition, while infrared brightness traces dust abundance and heating. Gradients across the disk can suggest where star formation has been sustained longest, and where inflow or mixing has altered the chemical record. The arm is not chemically uniform because it is constantly being stirred and replenished. The interaction that sharpened the arms also influences this cycle. Tidal forcing can drive gas into denser lanes and increase collision rates between clouds, which can raise star formation locally while also increasing turbulence that prevents complete collapse. Historically, the Whirlpool's companion has made it a natural laboratory. Early observers marvelled at its structure, and later astronomers used it to test ideas about spiral density waves and triggered star formation. The galaxy's beauty is therefore also a data set, refined by decades of improving instruments. As telescopes moved from photographic plates to space-based optics and sensitive radio arrays, the arms transformed from a visual wonder into a measured experiment in galactic ecology. The result is a controlled burn rather than a detonation. The Whirlpool converts gas into stars at a pace regulated by feedback, turbulence, magnetic support, and the continual rearrangement of gas by spiral dynamics. The arms look like stable architecture, but they are maintained by constant turnover. That turnover can be imagined as a river system, where gas flows in, is compressed into channels, pools into clouds, and then is splashed outward again by radiation and explosions. The river never stops, yet the shapes it carves can persist, because the pattern is continually re-etched. We return to the central question with a new emphasis. The hidden processes are not only dark matter and orbital dynamics, they are also the invisible states of gas, the shielding of dust, and the microphysics that decides whether a compressed cloud becomes a cluster. If we could stand above the disk and watch in accelerated time, we would see clouds assemble and dissolve like weather. Dust lanes would darken, then fray, while bright regions would flare and fade. The arm would remain, but its contents would be replaced again and again. The scene would feel both orderly and restless, like a storm track that keeps returning to the same coast, even though every storm is different. The arms are where the galaxy's engine becomes most legible. Gas enters as diffuse HI, becomes molecular in shielded regions, collapses into dense cores, and ignites into luminous clusters. Then feedback breaks the clouds apart and returns enriched material to the flow. Each step has a gatekeeper. Shielding allows molecules to survive, cooling allows density to rise, and angular momentum forces disks to form. Feedback then reopens the system, pushing matter back into the wider medium where it can begin another passage. Every stage has a characteristic timescale, and those timescales create tension. Massive stars light up quickly and die quickly, so the brightest regions are inherently temporary. The arm's beauty is therefore a snapshot of instability, a moment when collapse and disruption overlap. There is a deeper observation hidden in that overlap. The galaxy is not choosing between creation and destruction, because it requires both to remain dynamic. Without collapse, there is no light, and without disruption, the fuel would vanish into stars too quickly. To understand it, we cannot rely on one kind of light. We need optical to see exposed clusters and dust silhouettes, infrared to see embedded birth, and radio to see the cold reservoirs. Only by aligning these views can we place each region on the sequence from fuel to flame. When the views align, the offsets become a narrative. Dark lanes precede bright knots, and bright knots precede bubbles and shells. The arm becomes a moving cross-section through the star formation process, and M51 becomes a guide to what is otherwise hidden in our own galaxy. The chapter ends with a forward turn in the cycle. The newborn clusters do not stay quiet, and their most massive members are already counting down. Soon the Whirlpool's arms will become sites of death as well as birth, and the galaxy's life cycle will turn explosive. We drift onward along the spiral, following the brightest knots toward their aftermath. The same processes that create these clusters will also tear them open, leaving cavities, shock fronts, and enriched debris. The next chapter follows that violence and asks how a galaxy survives its own starfire. The Whirlpool's arms do not only build stars, they also build consequences that spread beyond each nursery. Along the bright ridges, creation and disruption travel together, like weather fronts that form, collide, and then roll onward into darker space. In wide-field views, the arms look calm and decorative, yet the physics underneath is restless and loud. In the last chapter, we followed gas into clouds and cores, then into newborn clusters. Now we widen again and treat the disk like an atmosphere. Energy moves through it as heat, momentum, radiation, magnetic stress, and fast particles. The spiral arms are not just patterns in starlight. They are corridors where those energies are injected, redirected, and sometimes vented away. If you could see pressure the way you see light, the arms would look like long, uneven storm bands. Think of the disk as layered. Near the midplane, dense clouds drift like storm cells, while above and between them a thinner medium carries pressure and turbulence. This vertical structure matters because density falls with height, so the same push produces very different motion. The spiral pattern compresses gas, but it also organizes the aftermath. So the arm becomes a repeating sequence of ignition, expansion, and clearing. In M51, that sequence is written into dust lanes, glowing arcs, and cavities that look almost punched through the disk. Star formation in M51 is rarely solitary. Most stars form in groups that share a birth cloud and a common clock. In the images, these groups appear as tight knots of blue-white light embedded in dusty lanes. Their shared origin matters because it synchronizes their evolution. So many stars begin influencing the environment at nearly the same time. A cluster is not only a collection of stars, it is a coordinated release of energy. Some groups remain bound as open clusters, while others disperse as loose associations. The difference is set early by density, gas removal speed, and the tidal field. If gas is expelled quickly, gravity loses its grip and the group unravels. If gas is removed more gently, or if the stellar density is high, the cluster can keep enough binding energy to persist. In other words, the cluster's fate is decided while it is still wrapped in its natal cloud. An open cluster is a temporary compromise between gravity and disruption. It can survive for tens to hundreds of millions of years, then evaporate. Even while it survives, it is not static. Its stars exchange energy through countless weak encounters, slowly pushing some members outward. The cluster's edge is not a sharp boundary, but a gradual thinning where escape becomes more likely. Encounters, internal relaxation, and the galaxy's tides slowly unbind members. Two-body relaxation is subtle in any single moment, yet relentless over time. The tidal field adds another pull. As the cluster orbits within M51, the galaxy's gravity stretches it, making the outermost stars especially easy to strip. Near spiral arms, where the gravitational field is structured, these tidal nudges can be stronger and less uniform. Associations are looser from the start and dissolve quickly into the field. Their stars drift apart at only a few kilometers per second, but that is enough. Over a few tens of millions of years, the association becomes a faint memory, smeared along the orbit and blended into the background disk. What looked like a single object becomes a subtle gradient of ages scattered across the arm. The clustered mode matters because it concentrates feedback. A single massive star can reshape a cloud, but a cluster can reshape a region. When several massive stars share the same neighbourhood, their radiation and winds overlap, and their supernovae arrive into cavities already prepared to transmit shock and heat. The environment becomes preconditioned, thinner, hotter, and easier for later energy to travel through. Many young clusters in M51 sit along the same arm segment, so their effects overlap. The arm becomes a chain of connected disturbances rather than isolated bubbles. Visually, you can imagine bright H-alpha arcs and scalloped shells stitched together, with darker dust pillars pointing back toward the light that is eroding them. In close-up, those pillars look like torn fabric, with bright rims where ultraviolet light is eating into the edges. To understand why clusters dominate the story, we need the initial mass function. The IMF is the statistical rule that sets how many stars form at each mass. It is not a single number, but a distribution, measured in nearby regions and inferred in distant galaxies through their integrated light. Historically, the modern form began with Edwin Salpeter's work in the 1950s, when star counts suggested a steep decline toward high masses. Later refinements added curvature at low masses, where faint stars become even more numerous. The IMF produces many low-mass stars and very few high-mass stars, yet the rare high-mass stars dominate luminosity, ionizing radiation, winds, and supernova energy. This is why a cluster's appearance can be misleading. Most of its mass is hidden in faint red stars, while most of its visible brilliance comes from a small, short-lived elite. In optical images, we mostly see the fireworks, not the fuel. This imbalance is the first source of tension. Most of the mass ends up in long-lived, faint stars. Most of the power comes from a handful of short-lived giants. The galaxy's visible sparkle is therefore driven by the least common members, and the timing of that sparkle is set by their rapid evolution. A spiral arm can look steady, even though its brightest contributors are vanishing almost as soon as they appear. Massive stars burn fuel fast because their cores run hot and dense. Their luminosity rises steeply with mass, so a modest increase in mass demands a dramatic increase in fusion rate. In plain terms, they shine so intensely that they consume their nuclear reserves at a furious pace. Radiation pressure also becomes important, and the star must balance gravity with an outward flood of photons. Their lifetimes can be only a few million years, shorter than many cloud-crossing times. They do not drift far from their birthplaces before they die. Their deaths therefore mark the same spiral segments that hosted their births, leaving behind cavities and enriched gas right where the next generation is trying to assemble. The arm becomes a place where youth and aftermath overlap in the same frame. Before the explosion, feedback begins with radiation and winds. Ultraviolet photons ionize hydrogen and raise gas temperatures to around 10,000 Kelvin. At that temperature, thermal pressure climbs and the ionized region expands, pushing against the colder neutral gas that surrounds it. The sound speed rises dramatically, so the gas responds like a suddenly heated atmosphere. Pressure rises and drives expansion into surrounding neutral material. The boundary becomes an ionization front, and it can be sharp, like a luminous shoreline where plasma meets shadow. Over time, the expanding region can sweep up a dense shell, while the interior stays hot and comparatively thin. In detailed imagery, the shell often looks clumpy, because real clouds are not smooth, and the front races through low-density gaps. Stellar winds add momentum and carve cavities that help radiation escape. These winds are streams of charged particles flowing off the star at hundreds or thousands of kilometers per second. When they collide with surrounding gas, they form wind shocks, heating the interior and inflating a bubble that can merge with its neighbors. The wind-driven interior can reach millions of degrees, although it is so tenuous that it is hard to see directly. In clusters, these early effects combine into larger cavities. Ionized regions overlap and merge, and wind bubbles collide. The combined cavity becomes a complicated interior of hot, turbulent plasma, with denser clumps surviving where cooling and gravity can still compete. Those surviving clumps are the seeds of the most dramatic silhouettes, dark knots with bright edges slowly being carved away. Dense gas is pushed into shells and pillars, while low-density channels open. The local medium becomes porous, and energy finds paths of least resistance. In the visuals, the arm's dust lanes look torn and sculpted, as if a hidden hand has combed the gas into ridges and cavities. The porosity matters because it determines whether energy is trapped locally or leaks into the wider disk. Then supernovae arrive and change the scale of the problem. A supernova is not just bright light, it is a rapid conversion of gravitational or nuclear energy into an expanding shock. In a few seconds, a star's core can collapse, rebound, and drive an outward blast that outruns everything around it. The flash is brief, but the mechanical consequences persist for tens of thousands of years. The shock sweeps up interstellar gas, heats it, and accelerates it outward. It is a moving wall of compression, and it does not merely push, it transforms. Cold gas becomes warm gas becomes hot plasma, and ordered motion becomes turbulence. The arm's neat dust lane can be turned into a shredded boundary between phases. We can describe the physics without equations. A shock front is a moving boundary, where supersonic flow is abruptly compressed. Kinetic energy becomes heat and turbulence. Behind the front, gas can reach millions of degrees, becoming a hot plasma that shines in X-rays and glows faintly in radio through energetic electrons. Even when the remnant is invisible in optical light, it can remain obvious in these other bands. At first, the shock is so fast that it barely notices the surrounding medium, but as it sweeps up mass, it slows, and the remnant's behavior changes. This is why supernova remnants have distinct stages, each with different observational signatures. The surrounding density, and whether the blast expands into a cavity or a dense cloud, can change the story dramatically. There are two main supernova channels. Core collapse supernovae come from massive stars that exhaust nuclear fuel. Their cores can no longer support themselves and collapse in a fraction of a second. The collapse is so rapid that electrons and protons are crushed together, forming neutrons and releasing a flood of neutrinos. Those neutrinos carry away most of the energy, and a small fraction helps power the explosion. The collapse rebounds and launches an explosion that unbinds the outer layers. The details are still an active research frontier, because the shock can stall and must be revived. Neutrino heating, turbulence, and instabilities in the collapsing core all appear to help the explosion succeed. In some cases, rotation and magnetic fields may also shape the blast, imprinting a symmetry on the debris. The remnant core becomes a neutron star or a black hole. A neutron star is a city-sized object with stellar mass and extreme density. Its magnetic field can be enormous, and its rotation can be rapid, turning it into a pulsar that beams radio waves like a cosmic lighthouse. A black hole forms if the core is massive enough that collapse continues past neutron support. Either way, the explosion enriches the medium with heavy elements. Those elements were forged in the star's interior and in the explosion itself, then scattered into the disk where they will later become part of new stars, planets, and dust grains. In a sense, the spiral arm is a conveyor belt for chemistry. Each generation leaves behind a slightly altered mix, and that mix changes how efficiently the next clouds can cool. Type Ia supernovae follow a different path. They involve a white dwarf in a binary system that gains mass or merges. When conditions ignite runaway carbon burning, the star disrupts completely. There is no surviving core, only expanding debris rich in iron group elements. Because the white dwarf is compact, the burning can race through it in seconds, turning much of its mass into heavy nuclei. Historically, astronomers separated these types by their spectra and by where they occur. Core collapse events trace star-forming regions because massive stars die young. Type Ia events can occur in older populations because their progenitors take longer to reach the critical conditions for explosion. This distinction became a cornerstone of extragalactic astronomy because it links a transient flash to the long-term demographics of stars. Both types release roughly 10 to the 51 ergs of kinetic energy. That number is abstract, but its meaning is simple. One event can outshine a galaxy briefly and can push on the interstellar medium for tens of thousands of years, long after the visible flash has faded. In a crowded arm segment, the cumulative effect is less like a single blast and more like sustained bombardment. In a clustered region, many events occur within the same cavity and add coherently. The first explosions excavate and heat, and later explosions expand into that lower density interior. Because cooling is less efficient in thin gas, more of the energy remains as pressure that can drive large-scale motion. The cavity becomes a resonant chamber for shocks, where each new event reinforces the last. A single remnant expands through stages. First, it expands freely while ejecta dominate. In this earliest phase, the debris moves almost ballistically, carrying the imprint of the explosion's asymmetries and the star's layered composition. Heavy elements can be stratified at first, then mixed by instabilities as the remnant evolves. Then it enters the Sadov-Taylor phase where swept-up mass matters and the shock decelerates. This is the classic energy-conserving stage, where the remnant's radius grows predictably with time. The shock is still strong, and the interior remains extremely hot, but the remnant is increasingly shaped by the density structure it encounters. A blast expanding into a cavity stays rounder, while one hitting clouds becomes lopsided and filamentary. Later it cools radiatively, forms a dense shell, and finally merges into the ambient turbulence. Radiative cooling allows the swept-up gas to compress into a thin layer, which can become unstable and fragment. What remains is not a neat sphere, but a disturbed region, folded back into the galaxy's broader turbulent cascade. The remnant becomes part of the background weather, no longer a distinct object. The key is that the hot phase persists longer than the flash. Even after optical brightness fades, hot plasma remains in cavities. It fills low-density regions and exerts pressure on surrounding clouds. This hot ionized medium becomes the background weather between denser structures, shaping how new clouds gather and how easily they can survive. In X-ray maps, it appears as a faint mottled glow that outlines invisible architecture. In M51, repeated supernovae in clusters create superbubbles. A superbubble is a large cavity formed by overlapping wind bubbles and supernova remnants. Its interior is hot, thin plasma with long cooling times, while its boundary is a swept shell that can be dense, wrinkled, and prone to breaking. The shell often carries the memory of the surrounding medium because it sweeps up whatever the arm provides. The shell is not merely a passive wall, it can collect molecular gas on its inner face, and it can develop instabilities that create fingers and fragments. In some places, it may compress gas enough to encourage collapse, while in others it may shred clouds and disperse them. When you see a bright rim with ragged edges, you're often seeing instability made visible. Superbubbles matter because they connect star formation to galactic-scale circulation. When a bubble grows large enough, it can break out of the disk. The vertical density gradient makes upward expansion easier than sideways expansion, because the gas becomes thinner with height and offers less resistance. The bubble is effectively climbing a hill of decreasing pressure, and that climb accelerates once the shell begins to rupture. The bubble vents hot gas into the halo through a chimney. Breakout can be dramatic. The shell ruptures, and the interior pressure finds an opening. In a multi-wavelength view, the disk shows bright rims and dark cavities, while above the plane faint emission traces the escaping hot component. The opening is rarely centered, because real disks are patchy, and the weak spot is wherever the shell is thinnest. A chimney is a channel that carries hot gas and metals above the star-forming layer. It is not a clean pipe, but a turbulent outflow. It can entrain cooler gas and dust, lifting them to high altitude, and it can also open escape routes for ionizing photons that would otherwise be trapped within the disk. Those photons can then affect gas far from the original cluster, extending the reach of feedback. This is how the disk breathes. Hot gas rises, expands, and cools as it moves into lower pressure. The process resembles convection in an atmosphere, yet driven by clustered explosions rather than solar heating. The halo becomes a mixing layer where disk material meets a larger reservoir. In Edge on Galaxies, we see this as faint, ghostly emissions stretching above the plane, hinting at constant exchange. Some of it escapes the disk-halo interface and mixes with the circumgalactic medium. Some of it cools, condenses, and falls back as a galactic fountain. The same event can therefore both remove fuel from star formation and, later, return it in altered form. The returning gas is not identical to what left, because it has been heated, diluted, and chemically enriched. A fountain is circulation rather than permanent loss. Gas launched above the disk can radiate energy and return on ballistic arcs. On the way down, it can seed new clouds, alter pressure conditions, and redistribute metals, so the cycle links local explosions to the long-term chemical and thermal evolution of the galaxy. The fountain also blurs boundaries, because disk material spends part of its life outside the disk. The fountain also changes angular momentum. Gas lifted into the halo can interact with halo material and magnetic fields. It can return with slightly different rotation speed and radius, and that small mismatch can accumulate into measurable mixing over time. Over many cycles, this can contribute to radial mixing and slow inward drift. The disk is not a closed carousel with perfect circular motion. It is a system where gas can be nudged, braked, and reinserted, slightly out of step with where it started. Those small offsets matter because spiral arms continuously reorganize the flow. The interstellar medium is therefore not only multi-phase, it is multi-directional, with flows along the disk and flows out of the disk. The arms are where energy injection is concentrated, so the weather is strongest there, but the consequences spread into interarm regions and into the halo. Even a quiet-looking interarm patch can be filled with old cavities, lingering cosmic rays, and magnetic tension. The disk's calm regions are often calm only in visible light. To follow this energy, we add two invisible actors. One is cosmic rays, high-energy charged particles accelerated in shocks. The other is magnetic fields, which thread the disk and couple to plasma. Together they make the galaxy a magnetized conducting fluid rather than a simple gas. This is a subtle shift in perspective, because it replaces purely thermal weather with electromagnetic weather. Cosmic rays are produced efficiently in supernova remnants. Shocks can scatter particles back and forth across the front, boosting energy step by step. This process, known as diffusive shock acceleration, turns a fraction of the explosion's energy into a population of relativistic particles that can travel far beyond the remnant. The particles do not move in straight lines, because magnetic irregularities scatter them like a fog of invisible mirrors. The result is a population of relativistic protons and electrons that diffuse through the disk. They carry energy far from the explosion site. Because they do not cool as quickly as hot thermal gas, they can store and transport pressure over long distances, smoothing the impact of clustered feedback. In radio maps, their presence is revealed indirectly as electrons spiral and emit synchrotron radiation. Magnetic fields guide that diffusion because charged particles spiral along field lines. The fields also store energy and exert pressure. In many regions, magnetic and cosmic ray pressures are comparable to thermal pressure, which means the disk's support is shared among several components that respond on different timescales. A cloud trying to collapse is therefore pushing against more than gas pressure alone. This changes how clouds collapse. Magnetic fields can resist compression across field lines and slow the gathering of mass. The resistance is not absolute because gas can slide along the field, but it can change the geometry of collapse, favouring filaments and sheets rather than spherical contraction. In high-resolution images of nearby clouds, those filaments are common, and M51 likely hosts the same hidden geometry. Cosmic rays can ionize dense gas and maintain coupling between neutrals in the field. That coupling can delay collapse and alter fragmentation, especially in shielded regions where ultraviolet light cannot penetrate. In plain language, cosmic rays can keep otherwise neutral gas slightly electrically sticky, allowing magnetic forces to matter deeper inside clouds. This is one reason cosmic rays are often described as a quiet regulator, present even where starlight is blocked. At the same time, magnetic tension can channel flows and shape filaments. It can also help launch outflows by providing a lever arm for rotating gas. In a superbubble, fields can drape around the shell and affect its stability, changing how easily the shell fragments into clumps. The field can behave like stretched fabric, resisting some distortions while amplifying others. The shell can fragment differently depending on field geometry. A field aligned with the shell can suppress some instabilities, while a tangled field can allow more chaotic breakup. These differences affect whether the shell becomes a site of new dense cloud formation or a shredded curtain that leaks hot gas. When the curtain leaks, the chimney forms earlier and the arm's energy escapes more efficiently. Cosmic rays also heat and pressurize diffuse gas. They can drive winds by adding a pressure gradient that pushes outward. Because they travel far, they can smooth energy input across large scales, so feedback is not purely local, even when the sources are tightly clustered. The Whirlpool's weather system is therefore layered. Cold molecular clouds sit in a warm atomic sea. Hot plasma fills cavities and leaks upward. Magnetic fields thread all phases and tie them together, while cosmic rays permeate the volume and add a long-range pressure component that is easy to overlook in visible light. In a composite view, you can imagine the cold gas as dark rivers, the hot gas as faint mist, and the magnetic field as an unseen scaffold that both guides and restrains the flow. Now we return to regulation, because the galaxy cannot survive without it. Star formation consumes cold gas, but feedback returns energy that can halt or redirect collapse. The balance is not a fine-tuned miracle. It is a set of feedback loops that tend to push the system toward a steady state, even as local regions flare and fade. The mystery is not that feedback exists, but that it so often lands in the narrow range between silence and catastrophe. One loop is negative feedback through dispersal. Radiation, winds, and supernovae can unbind a cloud before it turns much mass into stars. That limits efficiency and preserves fuel for later, while also stirring turbulence and raising effective pressure, which makes immediate recollapse more difficult. In practice, this means a cloud often dies young. It may form a cluster, then be shredded by the very stars it created. The arm segment remains active, but individual clouds are transient, cycling between assembly and destruction. The timescales are short compared with a galaxy's age, which is why the arms can keep renewing their pattern. Each generation is brief, yet the overall system persists. Another loop is positive feedback through compression. Expanding shells can sweep up gas into dense ridges. Where cooling is efficient, those ridges can fragment into new clouds. Triggering is not guaranteed, but it can propagate star formation along an arm segment, creating an apparent sequence of ages along the shock-compressed ridge. In images, this can look like a string of pearls, with younger knots tucked against the densest dust. The outcome depends on environment and timing. If the medium is dense and confined by spiral shocks, shells can accumulate mass and collapse. If the medium is porous and vented, energy escapes and clouds disperse, so the same cluster can both create and erase future star formation sites. This ambiguity is part of the arm's character. Each feedback event is a gamble with two possible outcomes. Self-regulation means the galaxy adjusts its star formation rate to its ability to cool and to confine feedback. If star formation rises, feedback rises and increases turbulence and heating. That tends to reduce collapse and bring the rate down, while if star formation falls, the medium cools and settles, making collapse easier again. The regulation is statistical rather than perfect, like climate rather than clockwork. This helps explain why M51 can sustain star formation over long times. The interaction with NGC 5195 can raise gas density and trigger bursts, yet feedback prevents the disk from turning all fuel into stars at once, so the arms remain bright but not catastrophic, and the galaxy avoids a runaway that would exhaust its reservoir quickly. The Whirlpool's beauty is therefore a sign of restraint as much as it is a sign of productivity. Regulation also shapes the disk's structure. Turbulence maintained by feedback thickens the gas layer and sets scale heights. Hot gas pressure can support a diffuse component that fills volume, so the disk becomes a foam of clouds and cavities rather than a uniform sheet. In some arm segments, the foam looks like a lacework of shells, where bright edges outline empty interiors. This foam is where the hot ionized medium matters most. Hot gas has long cooling times at low density, so it persists. It can percolate through gaps and connect cavities into networks, and those networks can act as highways for heat, metals, and cosmic rays moving away from star-forming sites. It can also carry metals and energy into the halo, linking disk physics to circumgalactic conditions. When we look at M51 in X-rays, we are seeing this hidden infrastructure. The brightest knots mark the hottest interiors, while fainter emissions suggest a broader, more connected hot component. The X-ray glow is not decoration, it is a map of where the disk has been hollowed out. Dust is caught inside this weather system, and does not always survive. Dust grains are robust in cold clouds, where collisions are gentle and shielding is strong. In hot plasma, grains are eroded by sputtering, where energetic ions knock atoms off the grain surface, slowly sandblasting solids back into gas. The process is microscopic, yet its cumulative effect can reshape the chemistry of an entire region. Over time, hot cavities can destroy a significant fraction of dust. The timescale depends on temperature and density, but the direction is clear. Where the hot phase dominates, dust becomes scarce, and the chemistry of the gas changes with it. Shocks can also shatter grains by grain-grain collisions. That changes the size distribution and alters how dust absorbs and emits light. Smaller grains heat more easily and can change infrared colors. So dust destruction is not only a physical process, it changes the galaxy's appearance, and it changes how efficiently the gas can cool. Cooling matters because it determines whether compressed gas stays warm and puffy or becomes cold and collapsible. Yet dust can reform and grow again in cooler regions. In dense clouds, atoms can stick to grain surfaces and build mantles. Coagulation can grow larger grains and change opacity. So dust is not only a tracer of gas, it is an evolving component that affects cooling, shielding, and molecule formation. In the darkest lanes of M51, dust is not merely present, it is actively shaping what the gas can become. This makes dust a participant in regulation. More dust improves shielding and promotes H2 formation. More H2 enables colder gas and easier collapse. Feedback that destroys dust can therefore reduce cooling efficiency locally and slow future star formation, coupling chemistry to dynamics in a way that is easy to miss if we only track mass and momentum. The arm's weather is therefore also a chemical weather, changing what the gas is made of and how it behaves. The heavy elements that make dust are also the products of supernovae. Core collapse events return oxygen and other alpha elements. Type Ia events return iron group elements. The mix changes with time and with the age distribution of stellar populations, so the chemical signature of feedback depends on which explosions dominate. In M51, clustered feedback therefore does two things at once. It injects energy that can disperse clouds and launch fountains. It also injects metals that make future cooling more effective once gas returns to dense phases, so the galaxy's weather both erodes and enriches its own fuel. The same blast that clears a cavity can also seed the next cloud with the ingredients for dust and molecules. This is where the story connects to cosmology. In the early days of galaxy modelling, simulations formed too many stars too quickly. Disks became too compact and lost angular momentum, and the virtual galaxies looked nothing like the extended spirals we see nearby. The missing ingredient was realistic feedback that could heat gas, drive turbulence, and launch outflows. As computational power grew, models began to include clustered star formation, supernova energy injection, and multi-phase gas. The goal was not to add fireworks, but to reproduce the self-regulating behavior that real galaxies appear to maintain. Modern simulations must include clustered star formation and supernova feedback to match observed galaxies. They must reproduce the Kennicutt-Schmidt relation between gas density and star formation rate. They must also produce realistic disk thickness, spiral structure, and multiphase media, because without feedback, galaxies do not look like the universe we observe. Feedback is therefore not a local detail. It is a universal ingredient that shapes galaxy evolution across cosmic time. It regulates how baryons settle into dark matter halos, and it controls how metals spread into halos and the intergalactic medium, influencing how later generations of galaxies cool and assemble. It helps determine which galaxies remain blue and which become quenched. A galaxy that cannot vent energy may consume its gas quickly, then fade. A galaxy that vents too efficiently may struggle to form stars at all, leaving a thin disk and a quiet, underluminous spiral. M51 is a nearby laboratory for these universal rules. Its arms show clustered star formation with clear age sequences. Its X-ray emission traces hot plasma in bubbles and along the disk, while its radio emission traces cosmic ray electrons spiraling in magnetic fields, revealing a pressure component that is otherwise invisible. Each band reveals a different pressure component in the same system. Optical light highlights young clusters and ionized shells. Infrared shows dust warmed by starlight, outlining where radiation is absorbed and re-emitted, while radio and X-ray reveal the energetic aftermath that continues long after the brightest stars have moved on. When we combine them, the whirlpool becomes a machine with competing reservoirs. Cold gas is the fuel, but it is fragile. Hot gas is the exhaust, but it can return through fountains, and magnetic fields and cosmic rays are the wiring and the hidden pressure that keep the machine from behaving like a simple fluid. The visible arms are only the surface of this engine. Beneath the starlight, the disk is a network of cavities, shells, filaments, and flows. The question is not whether feedback exists, but how it is routed, and which pathways dominate in different parts of the galaxy. The tension rises because regulation has a cost. Feedback can erode the cold reservoir by heating and dispersing gas. Outflows can remove gas from the star-forming layer for long periods, and if inflow from the outskirts and halo does not replenish it, the disk can slowly starve. In an interacting system, torques can also rearrange the fuel. Spiral shocks and tidal forces can move gas radially. Some gas is pushed outward into tidal features, while some gas is driven inward by loss of angular momentum, so the same disturbance that brightens the arms can redirect mass toward the center. This inward drift is not a single stream. It is many parcels losing small amounts of angular momentum through shocks, cloud collisions, and gravitational torques. Over time, those losses add up, and gas migrates to smaller radii where orbital times are shorter and gravity steepens. As gas moves inward, the environment changes. Shear increases, tidal forces strengthen, and pressures rise. Feedback becomes harder to vent sideways, so it vents vertically, and the disk halo circulation becomes more intense near the inner regions. The conditions begin to resemble a different regime than the outer arms. Clouds are squeezed by higher ambient pressure, and the balance between collapse and disruption shifts. Even the same physical processes, radiation, winds, supernovae, can have different outcomes when confinement is stronger and escape routes are fewer. In the inner disk, shells collide more often, and cavities overlap until the medium becomes a maze of hot channels and dense ridges. We can now restate the central question with new emphasis. What processes move energy through the whirlpool and decide whether gas remains fuel or becomes exhaust? How do clustered stars, explosions, magnetic fields, and cosmic rays shape the medium between clouds? And how does this weather prepare the inner galaxy for the next chapter? The arms sparkle because clusters form and massive stars burn briefly. The sparkle is also a countdown to shocks, cavities, and fountains. The whirlpool's beauty is therefore a moving balance between creation and disruption, and that balance is not guaranteed to hold as gas migrates inward. To understand it, we cannot rely on one kind of light. We need optical clusters to mark youth, infrared dust to mark heating and shielding, radio to trace cold gas and cosmic rays, and X-rays to trace the hot phase. Only then does the weather system become measurable rather than metaphor, and only then can we see how the phases exchange mass and energy. The chapter ends with a shift in emphasis. We stop treating feedback as a local aftermath and treat it as a transport system. Energy and metals move through cavities into the halo and back into the disk, while some gas loses angular momentum and begins a longer fall inward. Ahead, the spiral pattern still guides the flow, but the center imposes stronger rules. Gravity deepens, orbital periods shorten, and gas piles up under higher pressure. The question becomes less about whether stars can form, and more about what else can awaken when enough fuel reaches the nucleus. We follow the migrating gas toward the inner kiloparsec. The whirlpool's weather has been shaping the disk's future all along. Now it begins to feed the region where a hidden engine may already be waiting, and where the next transformation could be brighter, stranger, and far less brief. We have followed M51's arms as engines of compression, birth, and feedback. Now we follow the fuel that refuses to stay put. The camera that once lingered on bright knots in the arms begins to tighten its spiral. Dust lanes, like ink strokes on glass, curve inward and darken as the starlight behind them thickens. The luminous pinwheel starts to feel less like a postcard and more like a mechanism, gears turning inside a glowing shell. The central question tightens with the view, because the geometry itself becomes a clue. What physical processes move matter from a wide disk into a crowded nucleus, and what hidden power waits there? Gas cannot simply fall straight toward the center, even when gravity seems to invite it. In a rotating galaxy, angular momentum is the gatekeeper that blocks a direct plunge. A cloud on a near-circular orbit must lose orbital angular momentum before it can move inward. That requirement is not a technicality, because it is built into the symmetry of rotation itself, like trying to step inward on a spinning carousel without first letting go. Even if gravity deepens toward the core, the sideways motion stores a kind of orbital inertia that must be drained. Gravity pulls inward, but rotation keeps the gas suspended in a disk. The inward journey is therefore not free fall, and it rarely looks like a straight line in any map. It is a slow drift driven by forces that steal angular momentum and dissipate energy, often in repeated imperfect steps. Those forces must work against a stabilizing tendency, because circular motion is an efficient way to store orbital energy. In practice, the disk behaves like a self-regulating flow, where small nudges accumulate only after many revolutions. In M51, the forces are not a single mechanism acting in isolation. They are a layered set of torques, shocks, and viscosity-like processes that act over many orbits. Each step inward is paid for by an exchange of angular momentum with stars, gas, and the global gravitational field. The disk is not a static stage, because the potential itself is sculpted by patterns that rotate and evolve. When we say pattern, we mean a real gravitational imprint, mass arranged in a way that can tug persistently, not just a visual spiral. We begin with the simplest idea because it anchors everything that follows. If gas experiences a net torque that opposes its rotation, its orbit shrinks. If the torque adds angular momentum, the orbit expands. The disk becomes a marketplace where angular momentum is traded and mass moves in response. In that market, the currency is not money but momentum, and the price is paid in time. The trade is subtle on any single pass, yet it becomes decisive when the same lanes are crossed again and again. A torque is just a twist, but in a galaxy it is a twist applied by gravity. When the mass distribution is perfectly axisymmetric, there is no preferred direction to twist. Yet M51 is famous precisely because it is not perfectly symmetric, and the asymmetry is not cosmetic. Spiral arms, tidal distortions, and oval features create gravitational forces that do not point exactly toward the centre. That slight misalignment is enough to do work on the gas over repeated passages. The effect is cumulative, like a gentle but persistent hand guiding a spinning object off its original track. Shocks are one of the most efficient brokers in this exchange. When gas streams through a spiral potential, it can collide with itself and form shock fronts. Visually, those shocks often announce themselves as thin dust lanes, sharply defined against the glow of the stellar disk. In a shock, ordered orbital motion is converted into heat and turbulence, and energy is radiated away. The gas does not merely slow down, because it changes its internal state, becoming warmer, denser in places, and more chaotic in its motions. In molecular clouds, that chaos can broaden spectral lines, a measurable signature that the gas is being stirred rather than gently orbiting. A shock does not directly remove angular momentum by itself, and that distinction matters. It allows gas to change orbits by dissipating energy while torques do the bookkeeping. Together, dissipation and torque let gas settle onto a new, smaller orbit. Without dissipation, a torque can pump an orbit into a different shape without letting it settle. Without torque, dissipation can cool the gas but leave it circling at the same radius. The inward drift is therefore a partnership between gravity's twist and the gas's ability to shed energy. Cloud collisions play a similar role, though the collisions are not like billiard balls. In the outer disk, clouds can pass with modest interaction, because space is wide and the orbital crowding is gentle. In the inner regions, higher densities and crowding increase collision rates, and collisions act like friction. They stir turbulence, compress gas, and create transient high-density regions where molecules can form and cool efficiently. Each encounter can also scramble trajectories, turning coherent streaming into a more dissipative, inward-biased flow. Astronomers sometimes describe this as an effective viscosity, because it transports angular momentum outward. It is not molecular viscosity, which is far too small in interstellar gas. It is a collective effect from turbulence, collisions, and gravitational instabilities that couples neighbouring orbits. In plain terms, it is the disk rubbing against itself, not through atoms touching, but through clouds and eddies exchanging momentum. That rubbing is visible in patchy dust structure and in the mottled texture of molecular emission maps. This is the first stake increase, because it reframes the pinwheel as a machine. The same disk that looked like a stable spiral is also a conveyor that can feed its own centre. If enough gas is funneled inward, the nucleus can shift regimes from ordinary star formation to starburst conditions, and possibly to accretion onto a black hole. The threshold is not only about mass, because it is also about how tightly that mass is packed. Density changes the rules, cooling becomes faster, collisions become more frequent, and feedback becomes harder to escape. In M51, the companion galaxy NGC 55195 is not a distant bystander. Its gravity distorts the potential of M51's disk and drives asymmetries. Those asymmetries create tidal torques that can push angular momentum around on galaxy scales. The interaction is written into the whirlpool shape, and the shape is written into the gas flow. The famous grand design clarity is, in part, a fossil record of gravitational harassment. A tidal encounter does two things at once, and both are visible if you know where to look. It pulls out tails and bridges that advertise the interaction, like stretched taffy of stars and gas. It also reshapes the orbits inside the main disk, creating non-axis symmetric structures that can torque gas. The outer spectacle is therefore linked to an inner consequence, even if the inner consequence is harder to photograph. In simulations, the same perturbation that lifts a spiral crest can also tilt the phase of the gas response, changing whether torques feed the centre or stall it. The whirlpool is a case study of interaction-driven evolution, a theme that runs through modern galactic astronomy. Grand design spirals were once treated as static patterns, but decades of theory and simulations showed how companions can drive and maintain them. The same forcing that sharpens the arms can also push gas off circular paths and open channels for inflow. In that sense, the companion does not merely decorate M51, because it helps set the terms of its internal economy. The galaxy's elegance is partly the visible edge of a dynamical disturbance. To understand inflow, we need to separate stars from gas, even though they share the same gravitational field. Stars are collisionless and can cross orbits without dissipating energy. Gas is collisional and radiative, so when it is forced onto intersecting paths, it shocks and loses energy. That is why the gas responds more quickly to disturbances, and why it can settle into lanes and rings that stars ignore. The difference is fundamental. Stars remember their perturbations, while gas pays them off by radiating energy away. This difference makes gas more vulnerable to inflow, and also more informative to observers. A tidal perturbation can put gas on elongated orbits. Where those orbits crowd, gas collides, shocks, and settles inward, while stars keep their eccentric paths longer. The gas becomes a tracer of the galaxy's non-axisymmetric forces, because it cannot hide the consequences in long-lived orbital memory. In velocity maps, the gas writes the gravitational story in gradients and kinks. The inner disk therefore becomes a place where the galaxy's gravitational blueprint and its interstellar weather meet directly. Torques set the drift. Shocks and cooling set the ability to actually move inward. Cooling matters because radiating energy away allows compression to persist, and persistent compression is what turns a disturbance into a structural change. Without efficient cooling, the gas would rebound, and the spiral would be more a ripple than a conveyor. One of the most important torquey engines is a bar, and the concept has a long history in galactic dynamics. A bar is an elongated distortion in the stellar mass distribution. It rotates as a pattern and exerts gravitational torques on gas. In many galaxies, bars are obvious in near-infrared images, where old stars dominate and dust obscuration is less severe. Historically, the recognition that bars can drive secular evolution helped shift galaxies from static islands to systems that rearrange themselves over billions of years. M51 does not present a classic strong bar in the same way as some spirals, yet even weaker oval distortions, tidal bars, and M=2 asymmetries can play a similar dynamical role. The key is non-axis symmetry, not the textbook shape. A subtle oval can still twist gas orbits if it persists over enough rotations. In a disk that is constantly being perturbed, even a mild distortion can act like a long lever. In a barred or oval potential, gas responds by forming offset dust lanes and shocks along the leading edges. Those lanes can look like narrow, dark ribbons that cut across the inner light, and they often align with abrupt changes in velocity. Those shocks are where angular momentum is lost efficiently. Gas then streams inward along these lanes toward the inner kiloparsec. The flow is not smooth like water in a pipe, because it is clumpy and intermittent, yet the net transport can still be inward. In close-up views, the lanes appear braided and segmented, as if the disk is stitched by moving seams. The bar picture also introduces a deeper concept that complicates any simple narrative of steady infall. Inflow is not continuous to zero radius. It is regulated by resonances that reorganize orbits and can trap gas into rings. The galaxy is not only a funnel, because it also contains gates and holding tanks. Those gates are set by orbital frequencies, which means the flow depends on the rotation curve and the pattern speed, not just on how much gas exists. Resonances sound abstract, but they can be understood as traffic patterns in orbital motion. A resonance occurs when the frequency of a star or gas parcel's epicyclic motion locks into a simple ratio with the pattern speed of the spiral or bar. Epicyclic motion is the small in and out wobble that rides on top of rotation. In plain terms, it is how an orbit breathes as it goes around. When the breathing syncs with the forcing, the orbit's orientation can change systematically rather than randomly. Corrotation is the most intuitive resonance, and it divides the disk into two dynamical neighborhoods. At corrotation, the pattern rotates at the same angular speed as the material. Inside corrotation, gas overtakes the pattern. Outside corrotation, the pattern overtakes the gas. If you could hover above the disk, you would see the spiral pattern as a rotating scaffold, while the gas slides relative to it. That sliding sets where shocks form, because the gas meets the pattern at different angles depending on radius. This matters because the sign of torque can change across corrotation, and the gas responds to that sign. Gas can be driven inward on one side and outward on the other, depending on the phase shift between the gas response and the gravitational potential. That phase shift is subtle but decisive, because it determines whether gravity pulls slightly ahead of the gas or slightly behind it. Over many orbits, slightly becomes significant. The result can be a disk that simultaneously feeds its center and redistributes material outward, like a circulation system with multiple currents. Now we move to the inner Lindblad resonance, a name that carries the legacy of early 20th century celestial mechanics. The inner Lindblad resonance is where the natural epicyclic oscillation of an orbit matches the forcing in a way that changes orbital orientation. In plain terms, it is where the traffic lanes bend and crowd. The turning is not arbitrary, because it is set by the frequencies of motion in the potential. The resonance is a mathematical condition, yet it produces a physical structure you can often see. Near an inner Lindblad resonance, stable orbital families can switch, and the switch has visible consequences. Gas that followed one set of elongated paths may be forced to realign into a different set. Where those families intersect or crowd, gas shocks and piles up. The pile-up is not a gentle accumulation, because the gas is collisional and cannot pass through itself without paying an energy cost. The energy is radiated, the gas settles, and the crowding becomes a ring-like architecture. This pile-up often forms a circumnuclear ring. The ring is not a decorative necklace. It is a dynamical dam where inflowing gas stalls, compresses, and becomes dense enough for intense star formation. In images, such rings can appear as bright arcs of infrared emission, dotted with compact clusters and embedded sources that are still wrapped in dust. In the best maps, the ring is also a velocity feature. Streaming motions bend around it as if the flow has encountered a barrier. Rings can therefore be both endpoints and launch points, and that dual role is part of their mystery. They can halt inflow temporarily by storing gas at a resonance. They can also feed the nucleus intermittently when additional torques or instabilities move gas across the barrier. The ring becomes a reservoir whose level rises and falls, and the nucleus receives fuel in episodes rather than as a steady drip. The episodic nature invites a question: are we watching M51 in a quiet interval between surges, or in the build-up to the next one? In M51, observers look for these signatures in dust lanes, molecular gas ridges, and kinematic twists. The question is not only whether gas is present, the question is whether it is losing angular momentum fast enough to reach the center on meaningful timescales. A galaxy can contain plenty of gas and still starve its nucleus if the transport is inefficient. The difference between abundance and accessibility is the difference between potential and power. Timescales are the quiet constraint behind every claim, and they discipline the imagination. A mechanism can work in principle, but fail in practice if it is too slow. Inflow must compete with star formation that consumes gas and feedback that stirs it. It must also compete with the simple fact that orbits are long and the galaxy does not hurry. Even in the inner disk, the journey inward is measured in many rotations, not in a single dramatic plunge. A useful way to think about this is to compare clocks. The orbital clock measures how often gas passes through a spiral arm or a shock lane. The star formation clock measures how quickly dense gas turns into stars. The feedback clock measures how quickly young stars inject energy and momentum back into their surroundings. If the inflow clock loses the race, the gas is spent or scattered before it can reach the nucleus. If the inflow clock wins, the center becomes a collector, and the consequences can be luminous. In the inner kiloparsecs, orbital periods shorten, and that changes the rhythm of everything. Shear increases, and the gravitational potential steepens. Gas experiences higher pressures and stronger tidal fields, and its internal physics shifts. The same cloud that could survive in the outer disk may be stretched and shredded closer in, unless it becomes dense enough to hold itself together. The visual texture changes too. Dust lanes become more tangled, and the interarm regions look less empty. This is where the story begins to resemble the central molecular zone in the Milky Way, a comparison that is both tempting and instructive. The CMZ is a region of high gas surface density, high pressure, and strong turbulence. It forms stars intensely, yet in a way that is erratic and inefficient compared with naive expectations. That inefficiency is not a failure of physics, because it is a sign that multiple stabilizing forces are at work. In the CMZ, magnetic fields, turbulence, and shear can all help delay collapse, even when the raw material is abundant. A central molecular zone analog in M51 would show rising molecular gas densities toward the nucleus. It It would show higher velocity dispersions and broader line widths. It would show more frequent cloud collisions and stronger shocks. In spectra, those broader lines are a fingerprint of internal motions, because thermal broadening alone cannot explain them at the observed temperatures. The lines become a kind of seismograph, recording agitation in the gas that our eyes cannot see. High pressure changes the balance inside clouds, and the balance is delicate. It can compress gas to high densities, shortening freefall times and making collapse easier in principle. Yet strong shear and turbulence can also tear structures apart, making collapse intermittent. In plain terms, the gas is squeezed and shaken at the same time, and the outcome depends on which influence wins locally. The centre becomes a laboratory where competing processes operate at similar strength, and that equality is what makes behaviour unpredictable. This is the second stake increase, because the centre is not simply more of the disk. It is a different environment where the same ingredients behave differently, and where small changes in inflow can trigger large changes in luminosity. The nucleus is a sensitive detector of supply because it sits at the end of the transport chain. A slight increase in inflow can tip the balance from quiescent to active. The question, hovering behind the images, is whether the supply line is tightening or loosening right now. Star formation near the centre can be more intense because gas is denser and more confined. It can also be more chaotic because turbulence is stronger and orbits are less orderly. The result can be a starburst ring that flares, fades, and migrates. Even the location of peak activity can shift as gas piles up at slightly different radii when the pattern speeds and torques change. The ring is not fixed like a metal hoop. It is a living structure, shaped by the flow that feeds it. Feedback in this region is harder to vent sideways, and that changes its character. Dense gas and deeper gravity confine hot bubbles. Outflows may instead find vertical escape routes, linking nuclear activity to the halo. In edge-on galaxies, such vents can appear as chimneys of ionized gas, but in a face-on view like M51's, we infer them through kinematics and multi-wavelength signatures. The center can therefore influence regions far above the disk, even when the disk itself looks calm. Heating and turbulence become persistent, because the inner region is constantly being stirred. Shocks from orbit crowding, cloud collisions, and bar-driven inflow can heat molecular gas. Stellar feedback adds radiation, winds, and supernova energy into a smaller volume. The same energy that would disperse harmlessly in the outer disk becomes concentrated, and concentration is what turns energy into influence. In a crowded nucleus, even moderate power can reshape the medium because there is less room for the gas to evade it. Warmer molecular gas changes chemistry and emission, and the changes can be diagnostic. Some molecules become easier to excite, and dense gas traces brighten. The center becomes more luminous in infrared because dust absorbs intense radiation and re-radiates it. Dust grains act like tiny thermometers, glowing more strongly as they are warmed by young stars or by a compact central source. In close infrared views, the nucleus can look like a smouldering ember behind a veil, bright but partially hidden. Observationally, astronomers track this transition with multiple tools, because no single band tells the whole story. Infrared emission marks warm dust and embedded star formation. Millimeter spectroscopy maps CO for bulk molecular gas and HCN, and HCO plus for dense gas. These observations are often made with interferometers that synthesize a large telescope, turning faint line emission into detailed maps of structure and motion. The technique is itself a triumph of modern astronomy, many antennas acting as one, resolving what distance would otherwise blur. CO is abundant and relatively easy to excite, so it traces the molecular reservoir. HCN and HCO plus are not just labels, and they are not interchangeable with CO. They require higher densities to excite, so they highlight the gas most likely to form stars or to feed an accretion flow. When these lines brighten toward the center, they signal a shift in the gas regime, from widespread molecular material to compact high-density concentrations. In other words, they show not just where the fuel is, but where the fuel is becoming pressurized and ready. The ratios between these lines can also hint at physical conditions, though interpretation requires care. Higher HCN relative to CO can indicate a larger fraction of dense gas. It can also reflect changes in temperature, optical depth, or chemistry driven by shocks and radiation fields. The point is not to reduce the center to a single number, but to use multiple numbers to constrain what the gas is experiencing. In a region where processes overlap, the safest conclusions come from converging lines of evidence. Kinematic maps provide the most direct test of inflow, because motion is harder to fake than brightness. If gas were on perfect circular orbits, velocity fields would be symmetric and predictable. Inflow bars and tidal distortions produce non-circular motions, streaming, and twists in the ease of velocity contours. Those twists are like fingerprints left by forces that do not respect circular symmetry. The contours can bend into S-shapes, or kink near dust lanes, quietly revealing where the flow is being redirected. In M51, observers search for these deviations in the inner disk, and they do it with patience. They look for radial components in the velocity field. They look for shocks traced by dust lanes, and for abrupt velocity jumps across them. In some cases, the velocity changes align with the very dust features that mark compression, tying dynamics and morphology into a single narrative. The galaxy becomes readable as a layered diagram, where dark lanes, bright knots, and velocity gradients all point to the same underlying forces. They also look for asymmetries that betray the companion's influence, because tidal forcing rarely acts evenly. A tidal interaction can make one side of the inner disk respond differently than the other. That asymmetry can create lopsided inflow and uneven fueling of the nucleus. A lopsided nucleus is not merely an aesthetic oddity, because it can change where gas accumulates and where feedback breaks out. In extreme cases, the imbalance can persist long enough to shape the next generation of central stars. Now we enter the bulge and inner disk, where the stellar population changes as we move inward. The bulge is dominated by older stars, and their motions are less ordered. In visible light, the bulge often appears smoother and rounder than the disk, because it lacks the sharp dust lanes and young clusters that draw the eye. Yet its smoothness hides a more complex dynamical temperature. The light looks calm, but the orbits beneath it are more agitated. In the outer disk, stars and gas mostly follow near circular orbits, with modest epicyclic excursions. In the bulge, velocity dispersion rises, and random motions become comparable to rotation. The center becomes dynamically hotter. That heat is not thermal heat, but orbital agitation, and it changes how structures can persist. A cold disk can hold crisp patterns, while a hot bulge tends to blur them, even as it deepens the gravitational well. This matters for gas because the gravitational potential becomes rounder and deeper, and the tidal field becomes more punishing. Gas feels stronger tidal forces that can shear clouds. It also encounters a higher background of stellar mass that can torque it through non-axis symmetric structures. Even small departures from symmetry can matter more in a deep potential, because the forces are stronger and the timescales shorter. The same gentle twist that barely matters in the outskirts can become decisive near the core. The bulge is also crowded, and crowding changes the radiation environment. Stellar densities rise, and the radiation field strengthens. Dust is heated more easily, and the infrared background climbs. The center becomes a place where photons are plentiful, and where shielding becomes a key part of cloud survival. Dense gas must protect its molecules from dissociating radiation, which means the structure of dust and the geometry of clumps become part of the physics. The inner disk can host nested structures, and the nesting is a clue to the multi-step nature of inflow. A large-scale oval can feed a smaller nuclear spiral. A circumnuclear ring can feed a still smaller disk. Each step requires another loss of angular momentum. The pathway is therefore not a single ramp, but a series of ramps, each with its own physics. Seen in motion, it would resemble a set of interlocking streams, each handing material to the next. This nested inflow is where the mystery deepens, because our explanations become less secure as the scales shrink. We can explain how gas moves from tens of kiloparsecs to a few kiloparsecs, with spiral torques and tidal forcing. We can explain how it moves from a few kiloparsecs to hundreds of parsecs with bars, ovals, and resonances. But the final step, from hundreds of parsecs to a few parsecs, is harder. The mechanisms must change again, because the gravitational field steepens and the gas becomes more self-gravitating. At that point, the gas is no longer just responding to the galaxy, it is also shaping its own local potential. On these small scales, viscosity-like transport in a dense disk, gravitational instabilities, and feedback-driven turbulence may take over. A clumpy disk can exchange angular momentum through gravitational torques between clumps. Turbulence can act like a mixing process, moving momentum outward while allowing mass to drift inward. Yet turbulence can also thicken the disk and resist collapse, so it plays both ally and adversary. The same agitation that helps transport can also prevent the gas from settling into a thin, easily accreted layer. If an active galactic nucleus exists, it lives on these smaller scales hidden behind dust and distance. An AGN is powered by accretion onto a supermassive black hole. The energy release per unit mass is enormous compared with nuclear fusion. That is why even a modest accretion rate can matter, and why the difference between a quiet nucleus and an active one can be dramatic. The black hole's appetite is small in volume but vast in consequence. M51's nucleus has long been ambiguous, and ambiguity is part of its allure. It is not a blazing quasar. It may host a low luminosity AGN, or it may be dominated by star formation and shocks. The difference matters because an AGN can couple to the galaxy through jets, winds and radiation. A starburst can be powerful too, but it distributes its energy differently and on different timescales. One is a compact engine, the other a collective storm of many stars. Coupling is the key word because power without contact is only potential. A central engine is only transformative if its energy and momentum reach the surrounding gas. The question becomes how the nucleus communicates with the circumnuclear region, and how that region communicates with the larger disk. Communication here is not metaphorical, because it is carried by pressure, radiation, magnetic fields, and moving plasma. The center is a junction where these messengers overlap, sometimes reinforcing and sometimes cancelling one another. A starburst ring couples through supernova, winds, and radiation pressure, and it does so in bursts. It can drive turbulence and outflows. It can also consume inflowing gas before it reaches the black hole. In that sense, star formation can be both a sign of inflow and a competitor to it, because it converts gas into stars and locks it away. The ring can act like a hungry checkpoint, intercepting fuel that might otherwise continue inward. An AGN couples differently, even when it is faint. Even at low luminosity, it can launch collimated jets or fast winds. It can heat and ionize gas and change chemistry, producing line ratios that differ from pure star formation. Shocks driven by jets can compress gas in some regions while evacuating it in others, creating a patchwork of excitation conditions. The same nucleus can therefore both trigger and suppress star formation, depending on where the energy lands. Observers therefore compare diagnostics, because the nucleus rarely announces itself with a single unmistakable flag. Infrared spectra can separate dust heated by stars from dust heated by an accretion disk. Optical emission line ratios can hint at shock excitation, or AGN ionization. X-rays can reveal compact high-energy sources and hot plasma. Each diagnostic has caveats, but together they can narrow the possibilities. The method is forensic, assembling a case from partial clues, each distorted by dust and distance. Radio observations add another constraint, and radio has a special advantage. Synchrotron emission can trace cosmic rays from supernovae, but it can also trace jets. Morphology and spectral indices help distinguish these possibilities. A narrow linear feature suggests collimation, while a more diffuse glow suggests widespread star formation, though nature sometimes blurs these categories. In the radio, the center can reveal structures that optical light cannot, because radio waves slip through dust that would otherwise hide the scene. In M51, the inner region shows complex structure in multiple bands, and complexity is itself information. Dense gas appears concentrated. Dust emission brightens. Velocity fields show departures from simple rotation. The center looks less like a smooth disk and more like a crowded junction, where multiple streams intersect and compete. If the outer arms are highways, the nucleus is the interchange, ramps merging, lanes splitting, and traffic slowing where the geometry tightens. Each of these signatures can be explained by star formation alone, or by inflow alone, or by an AGN alone. The mystery is that they can also be the combined product of all three, interacting in a confined volume. When mechanisms overlap, they can mimic one another, and disentangling them becomes an exercise in careful inference. The most unsettling possibility is that the center is not in one state, but in transition, shifting as the supply line fluctuates. We return to the regulation problem from earlier chapters, now in a new form. In the arms, regulation prevented runaway star formation by balancing collapse against feedback and shear. In the center, regulation must decide whether inflow feeds a starburst, feeds a black hole, or is expelled. The decision is not conscious, but it is real, because it is encoded in competing rates of transport, collapse, and heating. The center is where those rates become comparable, and where small differences can tip the outcome. The companion's tidal forcing complicates that regulation, and it does so persistently. It can increase inflow and raise central gas density. It can also keep the inner disk asymmetric, sustaining torques that would otherwise fade. In isolation, a pattern might wind up and weaken, but interaction can keep the pattern supplied with distortion. The Whirlpool's present-day symmetry is therefore a paradox, an orderly face sustained by an ongoing disturbance. This interaction-driven inflow is a path by which galaxies evolve, and the idea has deep roots in extragalactic astronomy. Over cosmic time, repeated encounters can build bulges, feed central black holes, and transform star-forming disks. M51 is close enough to watch the process in detail, even if we see it in a single frozen epoch. The details we map here become test cases for theories that must also explain distant galaxies we cannot resolve. When we interpret a faint smudge at high redshift, we lean on nearby systems like this one to translate light into physics. We now connect the earlier hook to the present descent, because the narrative is a spiral too. The Whirlpool's beauty is not a still image. It is a carefully balanced engine that converts gas into stars while gravity rearranges the fuel. The arms that once looked like ornaments now read like conveyor belts, and the dust lanes read like the seams where the belts grip. The closer we look, the more the elegance becomes functional, and the more the function becomes unsettling. As we spiral inward, the engine's tolerances tighten, and the margin for error shrinks. The same amount of gas has greater consequences. A small inflow rate can sustain a nuclear ring. A modest change in torque can shift where gas piles up. The center is therefore sensitive to details that would be irrelevant farther out. It invites a quiet question. How many galaxies sit on the edge of such a threshold, waiting for a small perturbation to decide their next phase? The inner kiloparsec becomes a threshold region, and thresholds are where systems change character. It is where disk physics transitions into nuclear physics. Orbits become less like lanes on a highway, and more like crowded intersections with competing rules. The gravitational potential becomes steeper, the gas becomes denser, and the feedback becomes harder to ignore. The view compresses, and depth increases, as if the galaxy is folding inward on itself. Resonances create bottlenecks and reservoirs, and the bottlenecks can glow. Torques create drift, and shocks create dissipation. Feedback creates turbulence that can both hinder and enable further inflow. The same turbulence that supports gas against collapse can also mix angular momentum and help the next inward step, and that duality keeps the story unresolved. In a system this complex, the straightest path is rarely the one nature chooses. The observational story remains multi-wavelength, because the center hides behind its own products. Infrared brightness marks warm dust and embedded activity. HCN and HCO plus mark dense gas that is close to collapse or close to feeding the nucleus. CO maps the broader reservoir that must supply both. When these maps are layered, the center becomes a composite portrait of temperature, density, and motion. Each layer adds depth, and each also adds ambiguity, because different processes can paint similar patterns. Velocity fields reveal non-circular streaming that betrays torques, and the deviations can be subtle. Asymmetries hint at the companion's continuing influence. Together, these data let us infer not only where gas is, but what it is trying to do. The gas is not merely present because it is in transit, and transit leaves a measurable signature. The galaxy becomes a story written in vectors, not just in light. In this chapter, we do not resolve the nucleus, and we do not pretend to. We sharpen the question until it becomes unavoidable. Is M51's center quietly accreting, quietly bursting, or quietly preparing for a larger awakening? If the answer is all of the above, then the deeper question becomes how the balance shifts with time. The most important action may be invisible in a single image, because it unfolds over cycles of accumulation and release. The closer we get, the more the galaxy's center resembles a different kind of environment. It is an arena for extreme gravity, compact structures, and hidden energy release. The light becomes more concentrated, the dust lanes more tangled, and the sense of depth stronger, as if we are looking into a layered storm. The nucleus feels less like a point, and more like a region where the rules tighten, and where small distances separate calm rotation from violent change. We end with a forward turn, The inflow pathways we have traced are the supply lines to the final mystery. In the next chapter, we cross into the nucleus itself and ask what the central engine is and how far its influence reaches. We arrive where the whirlpool's graceful spiral tightens into a steep gravitational well, and the view subtly changes its meaning. The disk that looked like weather now feels like machinery under load, gears meshing, belts slipping, and heat building where friction cannot be avoided. Gas streams, shocks, and turbulence have delivered fuel inward, step by step, across structures that span thousands of light years. Now the question becomes unavoidable, because the centre is where small distances translate into extreme energies. Is the nucleus merely busy, or is it actively transforming the galaxy? Most large galaxies appear to host a central supermassive black hole, and this is not a poetic guess. It is an inference repeated across many systems, built from decades of increasingly sharp measurements and increasingly stubborn patterns. We see stars orbiting too fast near galactic centres, as if they are responding to something massive yet compact. We see compact radio and X-ray sources that fit no stellar explanation, because their luminosity varies too quickly for a star cluster. We see correlations between black hole mass and bulge properties, suggesting a shared history that links tiny central scales to galaxy-wide structure. Those correlations did not appear overnight, and they did not arrive as a single, decisive proof. They emerged as different techniques converged: stellar dynamics, gas kinematics, massive disks, and high-energy timing, until the same conclusion kept resurfacing. In nearby galaxies, improved angular resolution turned the nucleus from a blur into a measurable region, and the argument shifted from plausibility to constraint. When the same compact masses were inferred again and again, the simplest explanation became the most durable one. That historical arc matters, because the black hole idea was not always accepted as physical reality. Early on, dark stars and gravitational collapse were mathematical curiosities, and even after quasars were discovered, their power source remained uncertain. Only when observations began to resolve galactic centres, especially in nearby galaxies, did the case become difficult to escape. The modern picture is not that black holes are rare monsters, but that they are common relics of galaxy assembly. If that is true, then M51's nucleus is not an exception to the rule, but a test of how the rule behaves in a spiral galaxy with ongoing inflow. A black hole is defined by gravity, not by emitted light, and that definition is essential to the mystery. If it is not feeding, it can be nearly invisible, because it offers no surface to glow and no fusion to shine. Evidence comes instead from its influence on nearby motion, like wind revealed by the sway of trees. In the inner tens of parsecs, the gravitational field steepens, and the potential well becomes sharply curved. Orbital speeds rise, and the velocity field can reveal a central mass concentration that is too dense to be ordinary matter. In practice, astronomers infer central mass by mapping stellar and gas dynamics with painstaking care. Spectra provide Doppler shifts across the nucleus, turning colour into speed and line broadening into dispersion. Those shifts become a rotation curve and a dispersion profile, and they are compared against models of what stars and gas should do. The models test whether the observed motions require an additional compact mass beyond stars and gas, and whether that mass must be confined to a very small volume. The logic is simple in principle, yet demanding in detail, because every assumption about geometry can tilt the result. This is where uncertainty enters, and it is part of the tension rather than a flaw in the story. M51 is close, but its nucleus is complex and dusty, and the very material that feeds the centre also obscures it. Gas is not a perfect test particle, because it shocks, cools, and responds to pressure gradients that can mimic or mask gravity. Stellar orbits are not perfectly ordered, because the bulge is dynamically hot, with stars moving in many directions at once. The inferred black hole mass depends on assumptions about geometry, inclination, and the distribution of unseen mass, including faint stars and dark remnants. Even the act of measuring the centre is complicated, because the nucleus is not a clean point. Dust lanes cross the inner region like dark brushstrokes, and bright knots of star formation can pull the eye away from the true dynamical core. The central few arc-seconds contain overlapping components: molecular gas, ionized filaments, and compact clusters, each with its own motion. Astronomers therefore rely on multiple tracers, comparing stellar absorption lines, gas emission lines, and high-energy photons that cut through dust. The picture that emerges is probabilistic, a best-fit mass rather than a single, unquestioned number. Even with uncertainty, the central black hole concept matters for the central question, because physics becomes ruthless at small radii. A small region can dominate the energy budget if accretion is efficient, and efficiency is the key word. Fusion in stars converts a small fraction of mass into energy, and it does so slowly, regulated by the star's internal pressure. Accretion can convert a much larger fraction, because gravity does the work and releases energy as matter falls. That is why a faint nucleus can still be physically consequential, especially if much of its power emerges mechanically, rather than as visible light. To make that idea concrete, consider what falling inward really means near a black hole. In the outer galaxy, losing a little orbital energy changes a path by a modest amount, like drifting toward the center of a roundabout. Near the nucleus, the same fractional change in radius releases far more energy per kilogram, because the gravitational potential steepens dramatically. The center is therefore an amplifier, turning modest inflow into intense heating and radiation. It is also a gatekeeper, because only gas that can shed angular momentum will reach the deepest part of the well. Now we shift from evidence to mechanism. A black hole does not pull matter straight in like a drain, and that misconception hides the real difficulty. Angular momentum still blocks the direct plunge, and in a rotating galaxy, most gas arrives with plenty of sideways motion. Inflow from Chapter 5 must continue to shed angular momentum on smaller and smaller scales, from kiloparsecs to fractions of a parsec. The final approach is an engineering problem of transport, and nature solves it with turbulence, magnetic fields, and time. As gas falls inward, gravitational potential energy is released, and that energy does not vanish. It becomes heat, turbulence, and radiation. And it can also become bulk motion in winds and jets. The deeper the fall, the larger the energy per unit mass, so the inner regions are disproportionately important. Near the nucleus, the same amount of inflow can produce dramatically more luminosity, even if the inflow rate itself is not extreme. This is why black holes can matter even when they are not growing quickly. The gas forms an accretion disk because it cannot instantly cancel its sideways motion, and because collisions and shocks tend to circularize the flow. Streams intersect, compress, and radiate away energy, settling into a flattened, rotating structure with strong shear. Inner rings orbit faster than outer rings, and that differential rotation stores energy that can be tapped. Visually, it is a whirl within the whirlpool, an ordered spin threaded by chaotic flickers of turbulence. The disk is not a rigid plate, but a living flow, constantly rearranging itself. But a disk cannot accrete without losing angular momentum, and this is the central paradox of feeding a black hole. Something must act like friction, even in a near vacuum where ordinary viscosity is far too weak. The key driver is turbulence coupled to magnetic fields, and magnetorotational instability is the named mechanism. The idea is simple enough to picture. Weak magnetic fields link neighbouring rings, and shear stretches those field lines like elastic bands. The linkage transfers angular momentum outward and allows mass to drift inward, trading orbital order for heat. MRI turns ordered rotation into turbulent stress, and that stress behaves like an effective viscosity. The disk heats as it transports angular momentum, and the heating changes the disk's thickness and emission. The inner disk becomes hotter and denser, while the outer disk remains cooler and more molecular, with dust surviving where temperatures allow. The result is layered structure: hotter, more ionized gas inside, cooler, denser gas outside, and transitions that can shift as the accretion rate changes. In close-up, the disk would look textured, streaked, and restless, with magnetic loops rising and reconnecting. Accretion power emerges across the spectrum because temperature and density vary strongly with radius. The hottest inner regions emit ultraviolet and X-rays, and they can flicker on timescales tied to the small size of the emitting zone. Farther out, cooler gas and dust radiate in optical and infrared, adding a softer glow that can be steadier. Some energy is carried mechanically in winds and outflows, which may not shine brightly but can do significant work. The observed nucleus is therefore a sum of components, not a single light source, and each component responds differently to obscuration. X-rays are a crucial clue because they trace extreme temperatures and compact regions, where gravity's energy release is most intense. Hot plasma near the black hole can reach millions of degrees, and a tenuous corona above the disk can scatter photons to higher energies. Compton scattering and coronal emission can produce hard X-rays, and those photons can escape from regions that would be opaque to visible light. Even when dust blocks optical light, X-rays can penetrate, making them a diagnostic of hidden accretion. When we see X-ray variability, we're effectively timing the heartbeat of a very small engine. Infrared is the other key clue because dust absorbs and irradiates, turning invisible violence into warm glow. If the nucleus is buried, ultraviolet and optical photons are intercepted by dust grains, which heat up and emit in the mid and far infrared. The spectrum becomes a reprocessed echo of the central engine, smeared in time and softened in energy by the surrounding material. Obscuration can hide the nucleus in visible light, while revealing it in IR and X-ray, and this duality is part of why AGN can be missed in optical surveys. In visuals, the same region that looks calm in starlight can blaze in false-color infrared. This multi-wavelength logic echoes earlier chapters, but the stakes rise as we move inward. In the arms, dust hid newborn clusters and re-emitted their light, turning star formation into an infrared story. In the nucleus, dust can hide the accretion disk itself, and the hidden source may be far more compact and energetic. The same physics of absorption and re-radiation becomes more consequential, because the central engine can influence gas dynamics. The core can be active and still look quiet in optical images, like a furnace behind a closed door. Now we place M51 in the AGN taxonomy, without forcing it into a single box because nature rarely respects our categories. Active galactic nuclei range from quasars, so bright they outshine their host galaxies, to faint low-luminosity systems that barely stand out from stellar processes. A safer nucleus is bright in emission lines and often in X-rays, with clear signatures of hard ionizing radiation. A low-luminosity AGN can be weak, intermittent, and easily confused with shocks or compact star formation. M51 is not a quasar, and that fact is part of the mystery, because the fuel supply exists yet the blaze is muted. If M51 hosts a low-luminosity AGN, the accretion rate is modest, and the flow may not resemble the classic thin disk. The radiative efficiency may also differ if the flow is hot and geometrically thick, with energy trapped and carried inward rather than radiated away. In some regimes, energy is carried away mechanically rather than radiated efficiently, shifting the balance from light to motion. The nucleus can then be mechanically influential, without being optically dazzling, and that is a subtle but important form of power. It raises a question that hangs over the entire chapter. How much influence can a dim engine exert? Optical spectroscopy provides signposts through emission lines, because gas remembers what ionized it. Narrow-line regions form when gas is ionized by a hard radiation field, and the resulting line ratios encode temperature, density, and ionization state. Diagnostic diagrams can separate star formation from AGN-like ionization, though shocks complicate the picture by producing similar excitations. In M51, narrow-line emission and ionized structures suggest a central source that is harder than typical stellar populations, even if the continuum looks unimpressive. The lines are like footprints, showing where energetic photons have walked. Ionization cones are a key concept for geometry, and they turn obscuration into a map. If obscuring material blocks the nucleus in some directions, radiation escapes along others, often perpendicular to a dense disk or torus of gas and dust. The escaping radiation ionizes gas in biconical regions, carving luminous wedges through the surrounding medium. The cones trace where the nucleus can communicate with its surroundings, and they imply that orientation matters. What we see depends on viewing angle, and what we miss may be hidden behind a curtain of dust. This is the first peak of tension, because it forces us to separate appearance from effect. A nucleus can be present, but partially hidden and partially revealed, like a lighthouse seen through fog. It can look weak in one band and strong in another, because different photons take different paths out. It can ionize gas on tens to hundreds of parsecs, while remaining faint in optical continuum, leaving a bright signature without a bright source. The engine can be real and still be easy to underestimate, especially in a galaxy whose central region is crowded with other energetic processes. Now we turn to outflows, because feeding and feedback are inseparable at the center. Accretion does not only radiate, and it does not only heat the disk. It can launch winds from the disk surface, where gas is exposed to intense radiation and magnetic forces. Radiation pressure, thermal pressure, and magnetic stresses can accelerate gas outward, and the outflow becomes a channel that returns energy and momentum to the surrounding medium. In a sense, the nucleus exhales as it eats, and the exhale can reshape the environment that supplies the next meal. Jets are the most dramatic form of this feedback, and they are among the most visually striking structures in astrophysics. They are narrow, collimated streams of plasma launched from the inner disk region, likely tied to rotating magnetic fields and the spin of the central engine. Magnetic fields are the organizing structure, acting like rails that guide charged particles outward. Rotating fields can fling plasma along field lines, and the flow remains focused over large distances, even as it punches through surrounding gas. Jets are not guaranteed in every AGN, but when present they can dominate the coupling, because they deliver energy to specific places. A jet's impact is measured by what it does to surrounding gas, not by how bright it looks. It can inflate bubbles and cavities, pushing aside the interstellar medium like a piston. It can drive shocks that heat and compress gas, producing shells, filaments, and sharp edges in emission line maps. It can create radio lobes and X-ray emitting hotspots, where fast particles collide with denser material and radiate. Even a small jet can carve a signature in a dense nuclear environment, because the inner region is packed with gas that is easy to disturb. Outflows can also be broader and less collimated, and this is where the story becomes more multiphase and more complex. A nuclear wind can sweep material into shells and arcs, and it can entrain colder clouds, accelerating them imperfectly. The result is a multiphase outflow, with hot plasma, warm ionized gas, and cold molecular components moving together but not in lockstep. Each phase traces a different coupling mechanism, from direct ram pressure to magnetic draping to shock compression. In visuals, you would see a layered storm, hot gas filling cavities, warm filaments outlining edges, and cold clumps resisting like stones in a stream. We must distinguish AGN-driven feedback from starburst-driven winds, because the signatures can overlap. A starburst wind is powered by many supernovae and stellar winds distributed across a region, and its energy injection is extended and clustered. It is like the superbubbles of Chapter 4 scaled up, with many sources combining into one large outflow. An AGN wind or jet originates from a compact source and can be more directional, sometimes aligned with an axis set by the inner disk. Both can coexist, and both can mimic each other in some diagnostics, especially when shocks dominate the emission. In M51, the nucleus sits in an environment already shaped by inflow and by stellar feedback, and that context matters. Dense gas concentrations, shocks, and turbulence are expected from the transport pathways we traced, and the inner region is not a smooth disk. That means any nuclear outflow interacts with a medium that is clumpy and pressurized, full of density contrasts. The coupling is therefore uneven, producing localized shocks, patchy ionization, and filaments that brighten where the flow collides with obstacles. The center becomes a collision zone where direction and chance determine what gets hit. Now we focus on the extreme conditions near the nucleus, because the rules of stability tighten as gravity steepens. Tidal forces increase sharply with decreasing radius, and they can tear apart structures that would survive comfortably in the outer disk. A cloud that would be stable in the arms can be shredded here, stretched into streams and filaments by differential gravity. To survive, gas must be denser, more strongly bound, or supported by pressure and magnetic fields. The center becomes a filter that selects which structures can persist, and it favors compactness over fluff. Temperatures and densities rise, and chemistry changes with them, turning the nucleus into a different kind of laboratory. Shocks can heat molecular gas and alter line ratios, exciting transitions that are faint elsewhere. Cosmic rays and X-rays can penetrate deeper than ultraviolet light, changing ionization in shielded regions and driving unusual chemical pathways. Dense gas traces become especially important, because they reveal where the fuel is concentrated enough to matter and where collapse might still occur. In a visual montage, spectral lines become a coded language, translating invisible conditions into maps of brightness. Star formation in the immediate vicinity of an AGN can be suppressed or altered, and the reasons are physical rather than mystical. Strong shear can prevent collapse by stretching clumps faster than they can contract under self-gravity. Heating can raise the gene's mass and favour fewer, more massive fragments, shifting the initial conditions of star formation. Turbulence can both support gas and create transient dense peaks. producing brief opportunities for collapse amid overall disorder. The result can be a paradox of abundant gas and inefficient star formation, similar to the Milky Way's central molecular zone, where dense clouds exist yet form stars reluctantly. Feedback adds another layer to this suppression, and it can also create pockets of triggered compression. Ionizing radiation can destroy molecules and erode cloud surfaces, turning cold gas into warm ionized skins. Shocks can compress some regions while dispersing others, depending on how the shock meets the cloud and how quickly the gas cools. Outflows can remove gas from the plane or keep it stirred, preventing the calm conditions that collapse prefers. The nucleus can therefore regulate its own fuel supply, creating cycles of accumulation and disruption that look steady only when averaged over time. This returns us to the unresolved regulation problem from earlier chapters, but with the dial turned up. In the arms, feedback prevented runaway collapse while sustaining star formation, and the disk could vent energy into a relatively open environment. Near the center, the same feedback is confined by deeper gravity and higher pressure, and the gas cannot simply drift away. Venting routes change and vertical escape may dominate, with chimneys and fountains carrying energy out of the plane. The balance can shift from gentle self-regulation to episodic bursts, where long build-up is followed by short release. We now connect the engine to the galaxy's larger structure, because the nucleus is not an isolated room. Inflow from the disk supplies the nucleus, guided by torques, shocks, and the gravitational choreography of the interaction. The nucleus can return energy outward through radiation, winds, and jets, and that energy can change gas dynamics on scales larger than the nucleus itself. It can heat the inner disk, alter turbulence, and modify how spiral shocks compress gas, which feeds back into star formation patterns. The center can reach back into the system that feeds it, turning a one-way pipeline into a loop. If the nucleus is truly quiet, the inner disk may be shaped mostly by star formation and gravitational torques, with the black hole acting as a silent mass. If it is intermittently active, even at low luminosity, it can add a new feedback channel that is compact and directional. The difference is not only brightness, and it is not only a matter of classification. It is the directionality and coupling of energy to dense gas, which determines whether feedback strikes the fuel directly. A weak jet can matter more than a bright but isotropic glow, if it hits the right structures and drives the right shocks. This is the climax question in its sharpest form, and it is sharpened by the very complexity of the center. Is M51's center quietly feeding, with most energy trapped and re-radiated, leaving only subtle fingerprints in the spectrum? Or is it actively reshaping the inner kiloparsec through shocks, ionization, and mechanical outflow, even if the light output remains modest? The evidence can point both ways because the nucleus is a crowded intersection, and multiple processes leave similar marks. Starburst signatures, shock signatures, and AGN signatures can overlap, and the overlap is where interpretation becomes difficult. So we treat the nucleus as a system with competing rates, because rates determine outcomes more reliably than labels. Inflow rate sets the available fuel, and it depends on how effectively the galaxy can move gas inward. Star formation rate sets how much fuel is intercepted and locked into stars, converting gas into long-lived mass. Accretion rate sets the power of the central engine, even if that power is partly hidden or mechanical. Outflow rate sets how much fuel is expelled or recycled, and whether the center is being starved or merely stirred. The nucleus is the place where these rates become comparable, and where small changes can flip the outcome. We also treat it as a system with time delays, because the center is not a steady-state machine. Gas can pile up at resonances, then cross inward in episodes, as if gates open and close. Accretion can turn on and off as the inner disk reorganizes, changing its thickness, temperature, and magnetic structure. Outflows can clear channels, then fade as fuel drops, leaving cavities that slowly refill. The nucleus, we observe, is a snapshot of a cycle, not a permanent state, and cycles can masquerade as contradictions when seen only once. Now we widen to the cosmological relevance, because this nearby ambiguity is a universal problem, repeated across cosmic time. Across the universe, black holes and galaxies appear to co-evolve, and the evidence is statistical but persistent. The mass of the black hole correlates with bulge velocity, dispersion, and mass, implying a connection between the deepest potential well and the galaxy's stellar structure. That suggests feedback and growth are linked over billions of years, even if the coupling is indirect. yet the physical mechanism is still debated, especially in low luminosity regimes where the engine is subtle and the host galaxy is noisy. Feedback is a candidate mechanism for regulating galaxy growth, and its role depends on environment and scale. In massive galaxies, AGN feedback can heat halo gas and prevent cooling, leading to quenching and the long-term fading of star formation. In disk galaxies, weaker feedback may regulate central gas densities and star formation efficiency, shaping the inner structure without shutting the whole system down. The same principles scale with supply, geometry, and the state of the gas, from cold molecular inflow to hot ionized outflow. M51 offers a close laboratory to test how subtle nuclear activity interacts with dense, inflowing gas, and whether small engines can still steer large outcomes. Understanding M51 also helps interpret distant galaxies in the early universe, where everything is compressed into a few pixels. High redshift systems often show intense star formation and rapid black hole growth, but they are too small on the sky to resolve their nuclei directly. We rely on local analogues to translate integrated spectra into physical processes, separating what is due to stars from what is due to accretion. The Whirlpool lets us separate components that are blended in distant light, and it lets us test how obscuration and geometry can hide activity. It prompts a sobering question: how many distant normal galaxies might conceal engines we cannot yet isolate? Now we return to the documentary's opening hook, because the spiral's beauty has not changed, but our reading of it has. A beautiful spiral can be a balanced engine with a hidden power source, and balance does not mean stillness. The arms convert gas into stars and inject feedback into the disk, maintaining a turbulent equilibrium. The interaction with the companion drives torques that feed the center, tightening the spiral's flow into a smaller and smaller arena. The nucleus may convert a small fraction of that inflow into radiation, an outflow with disproportionate consequences, turning a trickle into leverage. This is where wonder and uncertainty meet, and where the narration should linger on what cannot be seen directly. The nucleus is not a single object, but a compact ecosystem, layered in temperature, density, and ionization. Gravity steepens, time scales shorten, and energy densities rise, so that processes that are slow in the disk become rapid here. The same physics of disks, turbulence, and magnetic fields appears again, but in an extreme regime where small differences matter. The center becomes a place where the galaxy's long-term evolution can be redirected, not by spectacle alone, but by persistent, focused influence. We end with a forward turn in time and scale, because reaching the center is not the end of the story. After reaching the nucleus, we pull back and ask how this system fits the larger cosmic story, where galaxies grow through accretion, interaction, and internal regulation. We place M51 within the history of galaxy formation, interaction, and transformation, and we ask what its current state foreshadows. The final chapter will widen the lens to deep time, connecting this nearby engine to the universe's broader pattern of growth, regulation, and change. The Whirlpool's beauty remains, but it now reads as a temporary balance, maintained by competing flows and competing feedback. Invisible gravity shapes the flow, tightening spirals into streams and streams into disks. Luminous starbirth marks the fuel's conversion, and the glow is both a celebration and a warning of consumption. Violent feedback vents the excess, carving cavities and stirring turbulence that prevents collapse from running away. A secretive central engine may be waiting, quietly feeding or quietly reshaping the galaxy from within, and leaving us to decide which kind of quiet we are witnessing. We linger one more moment on the measurements themselves, because the nucleus is a place where technique becomes part of the narrative. When astronomers map velocities, they are not just collecting numbers, they are reconstructing a three-dimensional flow from a two-dimensional projection. A tilted disk can masquerade as a slower rotation curve, and a warped inner structure can create apparent asymmetries that look like extra mass. Even the width of a spectral line carries multiple meanings. Thermal motion, turbulence, and unresolved rotation all contribute to the blur. The nucleus forces humility, because the data are rich, but the geometry is stubbornly hard to untangle. In visuals, this is where the camera would glide across a spectrum and the bright emission lines would split and broaden like a cord. A red wing would hint at gas receding, and a blue wing would mark gas approaching, while dust-darkened lanes would cut across the image like ink. Overlaid velocity arrows would reveal a pattern that is almost orderly, yet never perfectly symmetric. The impression is of a system trying to settle, while being constantly disturbed by inflow, feedback, and the galaxy's own asymmetries. The centre does not sit still long enough to be described by a single, clean diagram. The accretion disk, too, invites a more careful picture than the familiar textbook sketch. In the innermost region, orbital periods can be measured in days or even hours, so variability becomes a physical ruler. If the X-ray source brightens and fades quickly, the emitting region must be small because light itself has only so much time to cross it. That simple causality, size limited by light travel time, turns flicker into a constraint. The engine reveals its scale through rhythm, even when it refuses to show its face. Dust reprocessing adds its own timing, because warm grains respond more slowly than hot plasma. Infrared emission can lag behind changes in the inner disk, as if the surrounding material is hearing the engine and answering back. The echo's not perfect, because geometry matters and clumps intercept light unevenly, but the principle is powerful. A buried nucleus can still announce itself through delayed warmth, a soft afterglow that traces where energy was absorbed. In a crowded centre, those delays can help separate an accretion-powered source from a purely stellar one. When we speak of a torus or a dense disk around the nucleus, we should remember it is not a rigid donut floating in space. It is more like a thick, dynamic atmosphere of gas and dust, stirred by turbulence, radiation, and the gravity of the inner potential. Clumps form, collide, and shear apart, and the covering factor can change over time. That means obscuration is not just an orientation effect, it can be a weather pattern. The nucleus may hide and reveal itself in episodes, as clouds drift across our line of sight. All of this deepens the central mystery in M51, because the galaxy offers both fuel and complication. The interaction that drives inflow also stirs the inner region, and stirred gas is harder to model and easier to shock. Shocks can light up emission lines that resemble AGN excitation, while young stars can add ionization that muddies the diagnostic diagrams. The nucleus becomes a forensic scene where multiple culprits share fingerprints. The challenge is not to find a single signature, but to weigh a whole pattern of evidence, and that weighing leads back to a question that is more philosophical than it first appears. If a black hole is present but dim, is it irrelevant, or is it simply efficient in ways our eyes do not prioritize? If most of its output is mechanical, then the galaxy may feel it as pressure and momentum rather than light. If its activity is intermittent, then we may be catching it between outbursts when the engine is quiet but the environment still carries scars. The nucleus asks us to consider that influence can be delayed, directional, and subtle, yet still decisive. So when we pull back from the centre, the spiral arms look different, even though the photograph has not changed. The arms are no longer just decoration, they are supply lines, and the dust lanes are no longer just shadows, they are conduits. The bright knots are not only starbirth, they are also signposts of where gas has piled up and where it has been compressed. The nucleus sits at the end of that chain, a compact place where gravity can turn a little mass into a lot of consequence. In the Whirlpool, the hidden engine is not a separate story. It is the final Titan turn of the same spiral. We pull back from the nucleus and the whole Whirlpool reappears as one connected machine. The central question returns with new weight, because every bright structure depends on hidden dynamics. In a wide, multi-wavelength view, blue star clusters, pink H-alpha knots, and dark dust lanes lock together like gears. Even the empty-looking gaps have meaning, because gravity and pressure shape what the eye calls nothing. Start with the invisible frame. A dark matter halo sets the rotation curve, stabilizes the disk, and defines how strongly patterns can persist. Observationally, the clue is simple. The outer disk rotates too fast for starlight alone. The halo's mass distribution smooths the potential, reducing catastrophic instabilities while still allowing organized waves. Halo gravity does not draw spiral arms by itself, yet it sets the stage where tides and density waves can organize matter. In simulations, small changes in halo concentration can shift whether a spiral pattern survives for many rotations. Spiral structure becomes the next link in the chain. The arms are not fixed material, but long-lived patterns that crowd orbits and create shocks. Picture cars slowing in a traffic jam where the jam persists even as individual cars pass through. Gas, unlike stars, cannot simply cross unscathed, so it compresses and heats at the arm's leading edge. Those shocks compress gas, shift it into molecular form, and create the offsets that timestamp star formation. In M51, dust lanes often sit slightly upstream of bright young clusters, marking a delay of a few million years. Star formation follows the compression, but it never runs freely. Cooling, turbulence, magnetic fields, and shear decide which clouds collapse and which survive. Molecular gas must shed energy through radiation, yet turbulence keeps restirring it, and magnetic tension resists rapid collapse. Differential rotation stretches clouds, and tidal forces can shred them before gravity wins. The result is low efficiency, long-lived fuel, and a disk that avoids consuming itself. That inefficiency is not failure, because it is what keeps spiral galaxies luminous for billions of years. Feedback closes the local loop and opens the vertical one. Massive stars ionize, drive winds, and explode, injecting heat, momentum, metals, and cosmic rays. Ultraviolet photons carve cavities, while supernova blast waves accelerate particles that later glow in radiosynchrotron. Metals, carbon, oxygen, silicon, iron, seed new cooling pathways, and dust grains grow and shatter in the turbulence. Superbubbles vent through chimneys, feeding fountains that mix the disk with the halo. In edge-on analogues, those fountains appear as filaments and soft X-ray halos, like breath rising from a warm surface. Now the journey turns inward again, because feedback does not end the story. Shocks and turbulence dissipate energy, while non-axis symmetric gravity applies torques that trade angular momentum. Gas cannot fall straight in, because rotation acts like a barrier, so it must lose angular momentum first. Spiral arms and tidal distortions provide that lever, nudging orbits into slightly smaller radii each pass. Gas drifts inward in steps, piling at resonances, then leaking onward in episodes. Where resonances form rings, the galaxy writes its dynamics into geometry, and the ring becomes a record of where inflow stalls. The companion is the driver that makes this choreography durable. NGC 5195 perturbs the potential, sharpens the m=2 spiral, and sustains the phase shifts that create net torques. Historically, M51 became a classic case because early photographs already hinted at a tidal partner shaping a grand design. Modern numerical models reinforce that intuition, showing repeated passages that can refresh the pattern. The bridge and tails are not decorations, because they announce the same forces that reshape the inner disk. In a deep exposure, those faint streamers look like pulled silk, tracing the path of exchanged angular momentum. Inflow changes the center's rules. Higher pressure and shear alter cloud survival, and dense gas traces mark where fuel becomes compact. As gas piles up, collisions become more frequent, and the interstellar medium shifts from a patchwork to something closer to a pressurized fluid. The nucleus becomes a rate problem, where inflow, star formation, accretion, and outflow compete on short timescales. A small mismatch, slightly more inflow than consumption, can build a reservoir, then trigger a burst. That burst, in turn, can clear channels that temporarily shut its own fuel supply. Nuclear activity remains partly hidden, yet its influence can be real without being bright. A low-luminosity AGN or a compact starburst can ionize gas, drive shocks, and launch winds. In optical line maps, the ratios can shift subtly, as if the gas is being energized by something harder than starlight. The key question is coupling, because energy matters only when it reaches the surrounding fuel. If the energy escapes through a narrow chimney, the disk barely notices, but if it pressurizes the inner 100 parsecs, it can regulate the next inflow episode. This is the synthesis of the inward journey. Halo gravity enables stable rotation. Spiral organization compresses gas. Star formation converts gas to stars. Feedback stirs and enriches. Torques and dissipation drive inflow. The nucleus responds with bursts, winds, or quiet accretion. Seen this way, M51 is not a picture of a spiral, but a diagram of cause and effect. The visible pattern is the surface expression of competing timescales, each one ticking at a different speed. The life cycle of baryons links the whirlpool to cosmology. Gas arrives over time from the larger environment, conceptually from the cosmic web and from recycled halo reservoirs. Some accretion is cold and filamentary in theory, while some is warm and shock-heated before it can cool. It cools into the disk, forms molecules, becomes stars, and returns as enriched gas and dust. Each generation changes the chemistry, so later clouds form in a medium already seasoned by earlier explosions. When we measure metallicity gradients across the disk, we are reading a long history of transport and mixing. Outflows connect that cycle back to the halo. Hot plasma, cosmic rays, and entrained clouds carry energy and metals upward, where some material escapes and some rains back. The returning gas can fall at different radii, subtly redistributing angular momentum and smoothing gradients. The halo becomes both a memory of past feedback and a buffer that shapes future accretion. In that buffer, the galaxy negotiates with its environment, trading mass and energy across a boundary that is real in physics but invisible in starlight. What remains uncertain is not a footnote, because it sets the next decade of discovery. Kinematic signatures can be degenerate between inflow, streaming, and warped geometry. A velocity twist might signal gas spiraling inward, or it might be the projection of elliptical orbits in a strong spiral. Obscuration can hide the true power source, while shocks can mimic AGN-like line ratios. Even the most careful diagnostic diagrams can be fooled when dust and turbulence reshape the spectrum. Even our best tracers carry assumptions. CO to H2 conversion varies with metallicity and excitation. In dense, warm regions, the same CO brightness can correspond to very different true masses. Dense gas lines depend on temperature, optical depth, and chemistry. X-rays can be absorbed, and radio emission can blend jets with supernova-driven synchrotron. Every map is therefore an inference, and the inference is only as strong as the physical model beneath it. Next-generation instruments can tighten these links. Higher-resolution millimeter arrays can separate rings, spirals, and clumps in the inner 100 parsecs. With sharper beams, we can watch how gas crosses a dust lane, changes phase, and fragments into bound cores. Deeper X-ray and infrared spectroscopy can isolate accretion signatures from starburst heating behind dust. When the obscuring screen becomes measurable rather than assumed, the nucleus stops being a silhouette. Large surveys add the missing context of time and statistics. Mapping many nearby spirals across environments can show which features reliably predict inflow and nuclear activity. Comparing interaction stages can reveal how long tidal forcing sustains grand design structure. Some galaxies may show brief, bright responses, while others absorb the disturbance and remain quiet. The broader sample tells us whether M51 is an archetype, or a particularly well-lit moment in a diverse population. Now the perspective shifts to deep time. In the early universe, gas fractions were higher, disks were more turbulent, and interactions were more common. Clumpy star formation, thick disks, and rapid inflow were not exceptions, but typical conditions of assembly. What looks exceptional nearby may have been routine when galaxies were assembling rapidly. The Whirlpool's clean spiral, so easy to admire, becomes a late-time refinement of processes that once ran hotter and faster. That makes M51 a laboratory for distant epochs. Nearby, we can separate arms, shocks, and nuclei that would blur into 1 pixel at high redshift. We can test how offsets between dust and young stars translate into time delays, and how those delays change with environment. The Whirlpool lets us test how to read unresolved light as physics, rather than as mere brightness. It also invites a question. When we see a compact, luminous galaxy far away, are we witnessing a similar cycle, compressed into a smaller, denser stage? So we answer the central question directly. The Whirlpool is sustained by a balance between gravity, gas physics, and feedback, with the companion continually nudging the balance. Its beauty is the visible edge of invisible dynamics, written into motion and pressure. The spiral arms are not just scenery, because they are the galaxy's working surfaces. They organize gas, regulate star formation, and set the conditions for inward transport. The nucleus is not separate, because it is fed by the same patterns that shape the disk. The center is not an endpoint, but a node in a cycle. Matter assembles, ignites, enriches and returns, sometimes expelled and sometimes recycled. Over millions of years the pattern persists, and over billions it changes, as interactions and accretion rewrite the disk. Each passage of the companion is a reminder that galaxies are not isolated islands, but participants in a continuing exchange. In that exchange, structure is never permanent, only maintained for a time by the steady negotiation of forces. We end where we began, with a calm mystery about scale and time. A serene spiral is a temporary arrangement, held in place by forces we cannot see directly. In the Whirlpool, starlight and dust record a living process, and deep time keeps turning the page. The image feels still, yet everything in it is moving, slowly, relentlessly, toward the next version of the same enduring story. From 23 million years away, the Whirlpool has been our time machine, a fossil record written in delayed starlight and drifting dust. Its grand spiral is not painted on the sky, but continually rebuilt, shaped by a dark halo's gravity, sharpened by tidal passes of NGC 5195, and sustained as a density wave traffic jam that organises motion without being made of fixed material. Across the arms, we watched gas change phase like weather, from diffuse HI to cold molecular clouds traced by CO, then into brief, brilliant HRA regions and clustered blue stars that fade almost as soon as they appear. We also saw why the galaxy does not burn itself out, because turbulence, magnetic fields, shear, and imperfect cooling keep collapse inefficient, while feedback from winds and supernovae returns energy, metals, cosmic rays, and momentum to the disk and halo. That feedback does not simply explode outward, it chooses pathways. Some regions trap heat locally, others punch chimneys and fountains that vent into a soft X-ray halo, then rain material back down. And as we spiraled inward, the story became about loss, the slow surrender of angular momentum through torques, shocks, cloud collisions, and resonant gates that can stall gas in rings, or let it slip inward in episodes. The interaction that sculpted the arms may also be feeding the future, building central concentrations over hundreds of millions of years, preparing conditions for activity that feels sudden only because we see it mid-cycle. In the nucleus, certainty finally gave way to ambiguity, because dust hides geometry, pressure mimics gravity, and different tracers disagree on what the gas is doing. Yet even that uncertainty is a clue, because it tells us the centre is not a single object but a coupled system, where a compact engine, whether starburst, black hole, or both, must negotiate with dense gas, strong shear, and a constantly refilled supply line. The open threads we carried now converge into a single lesson. M51's beauty is the visible edge of invisible bookkeeping. The dark matter halo sets the potential that stabilizes the disk and allows spiral patterns to persist, while the companion's repeated passages likely tune the pattern speed, amplify the M2 symmetry, and leave signatures we can still hunt. Faint tidal streams, warped outer HI, asymmetric arm segments, and resonance-linked rings and arcs. The arms themselves answer the promise of how the pattern becomes luminous, because shocks and streaming motions compress gas, dust lanes mark the leading edge, and offsets between dust, infrared warmth, and H-alpha knots become a clock that times collapse across a few million years. But the arms are not a simple on-switch, because much of the gas survives each passage, held up by turbulence and magnetic tension, and because feedback can both trigger and erase star formation on the same map. The regulation problem, which once looked like a failure to make stars efficiently, becomes the mechanism that keeps the galaxy alive for billions of years. Even our hardest uncertainties fit the pattern, because CO to H2 conversion shifts with environment, X-ray absorption hides hard photons, radio emission blends compact sources, and kinematic twists can be inflow, or warped orbits, or streaming in a pattern. So the Whirlpool teaches humility alongside physics. The decisive tests are also coming into focus, because the next step is not one new image, but coordinated evidence. Higher resolution CO and dense gas maps to track true inflow, mesa or stellar dynamical constraints to weigh the central mass, time domain X-ray variability and infrared echoes to measure the engine's size, and spatially resolved line ratios and polarization to separate shocks from photoionization and to trace magnetic guidance. When those pieces align, we will know whether the nucleus is mainly a compact starburst or an intermittently feeding black hole whose power is mostly mechanical, shaping the inner kiloparsec with quiet jets, winds, and multi-phase outflows. And we will learn how strongly that power couples to surrounding gas, because the difference between regulation and runaway is not energy alone, but where it goes. So what physical processes, visible and hidden, build, sustain, and transform the Whirlpool from its arms to its extreme center? And what does that reveal about galaxies across the universe? The answer is that no single process is in charge, because a spiral galaxy is a negotiated truce between gravity's long reach, gas physics' short-range chaos, and feedback's constant attempt to rewrite the conditions for the next generation. What looks like a masterpiece is also a machine, but its gears are not metal. They are resonances, torques, cooling curves, magnetic fields, and the intermittent decisions of a central engine that may be dim in light, yet loud in momentum. If the opening question asked what's really happening at the center, the The deeper reply is that the centre is not separate from the arms, it is the arms' long-term consequence. Every orbit that shocks a cloud, every supernova that stirs turbulence, every tidal tug that shifts a pattern speed, and every resonance that traps or releases gas is part of the same conveyor, moving matter and information inward and outward across time. The whirlpool does not merely contain a hidden engine, it grows one, feeds it, and then lives with what it returns. In the end, M51 shows us that cosmic beauty is not a still image but a living process, an ever-changing balance that can hold for eons, then tip, then recover. And if a nearby galaxy can hide its true power behind dust, geometry, and uncertain traces, then the distant universe is filled with spirals that look calm, while quietly negotiating the same unstable peace. If you want to follow the next turn of that spiral, watch the new maps as they arrive, compare the wavelengths, and remember that every clearer answer will reveal a deeper question. The whirlpool is a machine, but its unseen strings are shared. Dark matter shapes the stage, tides pull the pattern, and feedback keeps the lights from burning out. At its centre, the deciding engine may be an obscured intermittent black hole or a compact starburst, yet either way it is fed by the same spiral